All right, I think we are getting ready to start. First of all, I want to welcome you all today to the Royal Swedish Academy of Sciences for this timely workshop on AI for science. We had sort of a bit of an exciting morning where the taxis getting the speakers to here thought they were going to the airport. So after that little accident was corrected, I think we're all good to go. My name is Ariel Gobar, and I'm one of the organizers of the conference, along with Justin Altsing sitting here, and here I am, Paris. I am a member, and of course with the great help from the people in the back, Peter and Pierre, who has been making sure that everything works. So I'm a member of the astronomy class of the Academy. I'm also the director of Oscar Klein Center, but more importantly, I'm also the principal investigator of the Educate Center of Excellence, which is co-hosting this event along with Academy. A few words about Academy. It was founded in 1739. And of course, it has the Royal Swedish Academy of Sciences has a proud tradition of promoting scientific excellence, fostering interdisciplinary collaboration, and contributing generally to the global scientific advancements. Best known, I guess, for everyone here is the fact that the Academy awards the Nobel Prizes in physics and chemistry. The Academy remains deeply committed to supporting emerging fields and groundbreaking research, such as the transformative intersection of artificial intelligence and science that we're here to explore. This workshop aligns perfectly with the goals of this Educate Center I was mentioning, which aims to integrate cutting-edge technology and data analysis into scientific research and education. By doing so, it enhances our capability to address some of the most challenging scientific questions of our time. AI, as we all know, has immense potential to accelerate scientific discovery, enable new insights across disciplines, and fundamentally transform the way we approach complex problems. So today we gather experts from very diverse fields, ranging from astrophysics, biology, energy research, material sciences, climate, etc., to share experiences, ideas, and strategies about harnessing the power of AI. Our hope is that this workshop will spark productive conversations, forge new collaborations, and inspire innovative research pathways. So thank you all for joining us at this exciting event. I look forward to engaging in discussions that lie ahead, and wish you a stimulating and fruitful workshop. So welcome all, and I pass the word to our chairperson, Justin Altsing.
Okay, great. So let's kick off the morning with our first talk, which is going to be Vignesh Gopakumar, who's here from the UK Atomic Energy Authority, to tell us about the confluence of two incredibly exciting fields, with AI and fusion in the same sentence. So welcome, Vignesh.
Thank you. Good morning, everyone. Extremely privileged to be here and honored to kickstart what I'm sure is going to be an exciting 2 days. So today morning, I'm going to talk about nuclear fusion. I'm going to talk about why we care, what the major challenges of fusion have been, and mostly like what we think the role that AI can play in helping us achieve sustainable fusion. So my name is Vignesh Gopakumar. I am an AI research scientist at the UK Atomic Energy Authority, but I'm also a PhD student at UCL. So my team at UKAEA, we look at everything from building simple classifier models up until integrating agentic workflows into our entire system. At the same time, my PhD cohort, we look mostly at probabilistic modeling for spatio-temporal processes. So most of the work that I'm going to discuss is an amalgamation of all of these, where some of the fundamental theoretical machine learning work that we do at UCL and through our collaborators, we implement at UKAEA and the larger fusion ecosystem. So why do we care? Honestly, the answer is just climate change. Global temperatures have been rising. We've slowly been creeping towards the tipping point of 1.5 degrees Celsius. And we have to start thinking about net zero past just a policy talking point. So there's been a whole range of potential energy sources that we can tap from. Why necessarily do we care that much about fusion? it mostly has to do with the fact that it's virtual inexhaustibility. It is the extreme high yield that fusion sort of provides is why we really want to chase this holy grail of energy. So just to give you like an idea of it. So from the water, the hydrogen that contains in the water from one bathtub and the lithium from 2 laptop batteries, we're capable of creating 16,000 energy from 16,000 wheelbarrows of coal, which is equivalent to like the energy usage of one person over 60 years of their lifetime. That sheer amount of energy that we can generate from something so little is the entire perception that we're going towards it. So even though we have a whole range of energy sources available, once we can crack fusion at a sustainable and commercial scale, we probably wouldn't need anything else. And it's that holy grail that we want to aspire and chase towards. So what is fusion exactly? Fusion is the combination of 2 lighter nuclei to form like a heavier, the nuclei of a heavier element. But when these 2 lighter nuclei sort of combine together, what happens is there is a slight change in mass. There's a reduction in mass. This mass is manifested as energy as Einstein's famous equation, E is equal to mc squared. So in this image, what we've got here is 2 isotopes of hydrogen. There's deuterium and tritium merging together to form a helium nuclide with a neutron and an release of excess energy. This was observed as the source of the stars and the sun by Arthur Eddington, a British physicist in 1925. This sort of like started sparking our curiosity. So if that's what powers the sun, which effectively powers half our energy sources on Earth, can we try and sort of capture that? We have this sort of vision or a phrase that we throw around in our labs called we're trying to build a star in our jar. What we're trying to create is, can we create like the sustainable fusion reactor in our backyard? So we don't have any sustainable fusion reactors in the world right now. This is our nearest sustainable fusion reactor, the sun. And this is what we want to try and create in our backyard. So if we've been chasing after this for mostly like, having knowledge of this for the past 100 years, why haven't we got there already? What's really the challenge? So fusion occurs due to the strong nuclear force, which has an extremely short interaction range. But these nuclei carry positive charges, and they're being forced close enough together, they tend to like push apart. So we have to fight against the electrostatic force in order to get to the attraction of the strong nuclear force, which takes a lot of energy. So I gave my 3-year-old nephew last summer this book called Nuclear Fusion for Babies. And this was his reaction when we sort of like got to that part. And honestly, I had the same reaction as well. Every time we have to solve the math to sort of get there. But obviously, it's not impossible. The sun does it. But the sun has a cheeky little trick. It uses gravity in order to sort of move past this electrostatic force. So fusion happens at the core of the sun. The entire mass of the sun pushes down onto the core in order to get past this electrostatic force and make fusion happen. So we have a way to build this, probably build a reactor as big as the sun, and we might get there, but we can't do that. So we have to decide on something else, which is to crank up the temperature. So the fusion triple product is for a certain amount of like confinement that we want in the plasma, we have to rely on density and temperature. Since we can't mess a lot with density or get it the same as that is in the sun, we have to actually start increasing the temperature. Which means in order for fusion to happen in our labs, the temperatures have to be hotter than the core of the sun, which sort of brings us to like the central challenge. But it is a challenge, but it comes with its own opportunities as well. And at such extremely high temperatures, the gas takes the form of plasma. These are ionized particles which can be controlled by an electromagnetic field. So this is our entire spiel, is that can we use magnets to control and confine this plasma? This is a general structure of what we call a tokamak. It is the magnetic confinement device that we conduct a lot of research on. We're building future fusion devices based on this. It essentially is composed of 3 quantities. There is the vacuum vessel, where the plasma is essentially confined and trying to be contained. And there are 2 sets of magnetic coils. There is the poloidal field coil and the toroidal field coils, which essentially create a helical magnetic field where we want to control and confine the plasma. So these things, this is just a bare bone structure, a very good children's illustration of this. But in actuality, they're extremely complex. So this is JET, which used to be the world's largest fusion device, which was decommissioned in 2023. This used to be in our lab. This is MAST Upgrade, which is the fusion device that we currently do a bunch of experiments on. And then we have ITER, which is a massive international collaboration that's being built in the south of France. There's also the likes of Commonwealth Fusion Systems ARC, which is a private fusion startup from MIT that's looking to build their own device soon. And we have UK's ambitious project, STEP, the Spherical Tokamak for Energy Production, where we're hoping to build not just a nuclear fusion experiment, but an actual nuclear fusion power plant and demonstrate it by the 2040s. Even though these things are complex with a million components sort of like dictating the nature of the plasma and the state of fusion, they're not impossible. This is our world record plasma from 2023, where from 0.2 milligrams of fuel, which is as much as a speck of dust, we could generate 69 megajoules of energy, which is equivalent of like boiling 500 cups of tea, which is a sheer amount of like energy to generate from something so small. But then again, the problem is that it only lasted for 5 seconds, which is a really short amount of time. That is what the major bottleneck has been. It's not that we can't make fusion happen, it's that we can't make it happen for long enough. So if I were to give you as what is the central takeaway challenge that comes from a fusion device, is that we have this thing called this temperature gradient to deal with. So at the core of our device, we have to heat the plasma up to 150 million degrees Celsius. And at the first wall, at the border, we have what is essentially the highest melting point known to man, which is about 4,000 degrees Celsius for tungsten. So within a span of a meter, we have to go from 150 million degrees Celsius to 4,000 degrees Celsius, which is a very steep temperature gradient that we have to sort of like fight and balance along. The plasma doesn't like to be confined together. It wants to push apart, but we have to use magnets to sort of push it back. This delicate balance manifests as a bunch of challenges that comes along. There's materials that we have to focus a lot on, which has to deal with these excessive heat loads. We also have to think about how we will provide the fuel for it. How do we line these materials in order to like make fusion sustainable and carry forward? The physics regime that we operate in the plasma is extremely nonlinear and complex. It operates at multiple scales and at multi-physics scenarios, that it is difficult for us to understand the full complexity of it to begin with. Which brings us to confinement, which is the sharp temperature and pressure gradients, and how do we structure the exhaust so that we can remove the impurities and the excess fuel that sort of comes along. So these are the major challenges that sort of like comes from fusion research as it is. So what's happened in the past 5 years? What can AI really do to help? And to be honest, a little bit of everything. It sort of helps us solve all of these challenges a little directly, some of it a little indirectly. And we've sort of taken this approach where AI for fusion broadly works out to these 4 pillars. And I'll get to each in detail as to each of how these pillars are sort of structured and how AI helps in them. So AI can help us model better. They're better predictive tools. They give us a new sort of method for control, also opening up an entirely new paradigm for design. So fusion research is at a particularly sort of interesting space right now, where we call being at the bottom part of the engineering S-curve. So if you were to think that reusable rockets are at the top part of the engineering S-curves, those likes of SpaceX, where they've been demonstrated technology, they can see its commercial value, they're sustainable, fusion's sort of starting to climb that path. But we can't do what reusable rockets have done. We can't afford to sort of build reactors, break them, build them again, just because they're too costly and expensive. We have to think about some other ways. We also don't have the time for it. Net zero is something that we have to aspire for as soon as possible. And if we see fusion as a significant tool in that arsenal, we have to sort of work beyond those timescales as well. So which means that we have to start thinking about simulating everything. We have to go in silico and try and understand as much of the physics and the materials in control as possible. And we can do these simulations. These simulations are sort of possible, but they're also slightly expensive. They're also across a broad range of like multi-physics scenarios and multi-scale, that even doing them at a phenomenal exascale might be a bit of a challenge. So in this sort of simulation, what we have is these plasma blobs are studied under the influence of when a magnetic field is sort of removed. When we sort of quickly remove the magnetic field, we want to understand how the turbulence would sort of emerge, how the plasma goes and interacts with the wall, and the reaction that sort of comes from it. So these simulations themselves are fairly expensive on like multi-complex supercomputers to sort of dress towards. So what could we sort of like look at? How could AI help on this? And this is sort of the first angle that we played with is, can AI help us accelerate simulation? So we came up with this whole framework for like surrogate modeling scenarios where what we want is the same way that we treat numerical solvers, we take its initial conditions of boundary, the geometry definitions, the definitions of the PDE, and we feed that into like a numerical solver. Can we take that data that emerges from these numerical solver and embed that into an AI-driven model, what we call a surrogate model? And we've devised this entire surrogate modeling framework as sort of the first point of attack. It's not to say that it's removing numerical solvers altogether, but we structure it in such a way that when you actually have to study a new physics, we go first to the surrogate model, see if it's giving us a good enough solution, and depending on the quality of it, we go back to the numerical solver. So we applied this whole methodology to a range of problems. We started with magnetohydrodynamics, which is a combination of Maxwell's electromagnetic equations as well as Navier-Stokes. Pretty challenging problem to look at. And we found that our neural PDE solvers, such as an FNO, which was deployed in this case, can actually approximate the MHD behavior about 1,000,000 times faster than the traditional numerical solver. It's capable of understanding the higher order trends of the turbulence and the interactions with the walls that comes along. Each simulation actually took about 350 core hours, where training this entire model took only less than 10 hours on a single GPU. And we could clearly see this as like a first point of attack, where we should look at these AI models to help us accelerate these simulations. We then applied this to a bunch of other complex simulations as well. I'm sorry, I think I seem to be missing a few slides. It's okay. My flow just went off. We did apply to a bunch of other complex scenarios which seem to be missing from these slides, where we applied for gyrokinetic behavior and we look at complex five-dimensional gyrokinetic circuits as well, and we're able to get like matching accuracies, and then that leads us into an active learning pipeline where, because generating this data is expensive, so we needed to make sure that we do an informed sample of the parameter space as we structure into this as well. So that brings me to the next sort of phase, skipping through those slides, is that simulations might not be fully representative of the experiment as well. There is this sim-to-real gap that exists for a variety of reasons. A, that we might not be able to replicate everything that we want in the experiment. There's diagnostic measures that we have to consider. There's also some of the physics that we don't really understand. So we needed to try and like look at ways to bridge this sim-to-real gap. We noticed that the experiment data might be noisy, sparse. So how do we sort of structure along this? So we started going back to our experimental data and see what AI could sort of build with this. So we've been working a lot with NVIDIA over this to see how we can create like a full digital twin of the device. And it turns out we can build fantastic digital twins for like real-time predictions. Actually, this is even faster than real-time. So here what we're looking at is the plasma as seen through the visible camera in front of the device. And on the left, we have the camera model, sorry, the actual camera. And on the right, we have the FNO, which is the surrogate model that we've chosen for this. What the model actually does really well is it predicts the confinement state. It sees how the plasma is interacting with the wall, all while being quite ahead of the plasma. So we can actually learn the causal relations which come from like the plasma state to predict what sort of phenomena we'll observe as the plasma comes through, which is really helpful because it helps us forecast in real time different kinds of plasma events. On the left, we have something called an LH transition. So the LH transition is something that basically goes from a low motor confinement to a high motor confinement. And high motor confinement is something that we really want and we really like, but we don't understand like what sort of drives us towards these H motor confinement as well. Well, these predictive models have actually been helpful in understanding that, giving us sort of like a scientific inquiry, but at the same time, giving us a tool to sort of help us push our plasma towards that. And on the right, we discuss something called a disruption. These disruptions are nasty events. It's basically what happens when we have a total loss of plasma control. So that energy is absorbed by the walls. It sort of picks up as eddy currents on these walls, and it lifts the device up by a few inches and drops it to the floor. They're nasty because they create a mini seismic event depending on the size of the device, but also they're quite damaging to the diagnostics and the internal wall of the device, so we kind of really want to avoid that. And machine learning has been fantastic in actually identifying when these disruptions will occur, so in quite ahead in real time, we can create actuator responses to control and confine the plasma so that it doesn't end up in a disruption. This has been helpful because now we've been able to do modeling We can do prediction, which sort of like helps us, gives us tools to like look at control. So plasma control broadly comes around to 4 aspects. There's the magnetics that we really care about and how do we sort of supply the energy to it. There's the heating, which is just the amount of temperature and then the plasma energy that you kind of want, as well as the fuel, which is the amount of deuterium, tritium, the other kind of gases that you would like to provide, and of course the exhaust, which is extremely important because we want to take out excessive heat, the impurities, as well as the byproducts of fusion. Even though it's 4 elements, it sort of is controlled by thousands of parameters. And in order to have a long, sustained, confined plasma, we require like an extensive prophetic knowledge of the plasma as to how it will evolve. So some of our colleagues at Google DeepMind and EPFL are actually taking a stab at this problem, where they trained a reinforcement learning algorithm to sort of see if they can control the plasma equilibrium in real time. So what they did here is they gave control access to the model, the access to the voltages of the magnetic field coils, and defined what ideal equilibrium they want. By equilibrium, we mean the shape of the plasma, its position within the device, how the magnet should structure and confine that scenario, and maintaining stability for a decisive sort of period in time as well. And it actually worked fantastically well. And they demonstrated this on like an actual fusion device, observing even newer modes of configuration as well to sort of understand and deeply dive into the physics. But I did mention STEP to start with. STEP is this bold, ambitious project that we've got where we are rethinking the different concepts of a tokamak, which also means that design is an open question. It's a very high-dimensional, multi-objective optimization problem that we need to sort of tackle there. But one of the big challenges is that we can't explore the full parameter space. Even if we go in silico, even if we use our full suite of like simulations and models, it is quite expensive and we will not be able to explore that full space in real time. So we took a stab at like maybe we can use an Bayesian optimization toolkit to actually explore that space. So here, in this particular scenario, we took at what the positions of these blue boxes, which are these magnetic field coils, need to be in order to get a desired confinement and desired plasma equilibrium. We actually were able to demonstrate that we can reduce our simulation time by about 50% by just doing an informed sample of this entire simulation space. But working in fusion, one of the key things that we keep looking at is that we're in a very safety critical sort of space. We need to make sure when we deploy these models, it's not just that we know what they know, we also really need to know what they do not know. So we've looked at a plethora of uncertainty quantification methods that need to be embedded into these into all of these models that we consider as we deploy them. So we have a bunch of like very traditional Bayesian, frequentist, and verified methods that we deploy to make these models actionable. We've also been trying to develop like novel uncertainty quantification methods as well. So over here, we've actually come up with a novel conformal prediction framework which can handle like spatio-temporal data and give us like valid, rigorous error bars, which are really helpful in understanding if this predictive model is works well within the regime we're interested in, or should we just go back to like training a model from scratch. We've also looked at if we can build, take information from our knowledge of the PDE and sort of factor that in as a measure of uncertainty. So we've taken insights from PDE analysis and factor that into like methods of quantifying the uncertainty for surrogate models that are catering towards simulation. And over here, what we were able to demonstrate is that by doing this physics residual error analysis, we can actually get very similar to what the absolute error on predictive models look like without requiring any data, without requiring any other further calibration as such. So to sort of summarize, AI can help us accelerate simulations. It's helping us bridge this sim to real gap across simulations and experiments. It's giving us a new tool for prediction. It's the fact that we can actually predict, in real time predict a full range of plasma behavior. And it's giving us a new agentic method of controlling the plasma, which is, it's giving us a lot of insights into like how the different nonlinear regimes behave within the plasma, plus also taking a little bit of the heat away from actually us devising short campaigns to like larger, longer campaigns. It's also changing the way that we do design. It's giving us methods for efficient exploration of like high-dimensional, multi-objective design space as well. So it's often joked in my industry that fusion sort of is like always 30 years away. But honestly, seeing the developments that we've had in the past 5 years, we have a feeling that it just might be this time. Thank you.
Okay, so welcome to the second talk of the day. So it's a pleasure to have with us Jean Kossaifi, who's jet-lagged all the way from San Francisco, from NVIDIA, from one of the most exciting research programs in the world on accelerating physical simulation, among other things. So take it away, Jean.
Right. Thank you for the introduction. My name is Jean Kossaifi. I'm a senior research scientist at NVIDIA. And thank you to the organizers for the invitation. It's a really great symposium. And so really glad to be here today. I'm especially glad that my talk was scheduled after the coffee break. So I hope you're all at peak caffeination levels and ready to hear about AI for science and engineering. So it's a priority for us at NVIDIA, and we're building a research effort around it. And so today I want to talk to you about the key concepts around it. So it's also really nice that it comes after the talk of my colleague Vignesh, a really great talk on AI for fusion, and he kind of touched on the use of neural operators. So now I want to dig in a bit about what neural operators are and what it means in practice. And so since we're in the home of the Nobel Prize, I figured I would go back to where it all started. When the Nobel Prize for Hinton and Hopfield was announced, the most interesting part for me, probably the most surprising part for me, was that it was a Nobel Prize for physics. And it actually makes sense because Boltzmann machine and Hopfield networks directly use concepts from physics to solve problems in learning and memory. And so after this, for about 30 years, the field built on this physics foundation, but the focus shifted from modeling physical systems to actually solving problems in perception, typically vision or language. So then we had a bunch of innovations like backpropagation, which made it possible to train deep neural networks. We had the first practical application of convolutional neural networks by Yann Lequin. But really, the tipping point was in 2012 when three things came together. We had new algorithms that built on all those foundations. There was AlexNet, trained on very large data sets. So there was the ImageNet that was introduced by Fei-Fei Li just a few years before. And those were trained on GPU-accelerated computing. And so these three things made it possible to have this so-called AI revolution. And then later, we have kind of had a move away from inductive biases towards more general architecture with attention. And so now we're seeing the story come full circle where the tools that grow out of physics have matured enough that we can now try to apply them to accelerate some problems in science and engineering. So one issue, however, with this evolution is that historically, models have been designed for the discrete world with, for example, fixed-sized pixel images or language, like discrete tokens. And as you know, scientific data is typically a little different. We have different boundary conditions, different geometries, and interesting phenomena happened at multiple scales in nature. They're typically governed by some mathematical equations, partial differential equations, in some cases known, in others not. For example, we may want to look at the velocity and temperature of a fluid heated from below with some Rayleigh-Bénard convection models. We may want to look at the flow around the car, measure the drag, or we may want to look at things like weather forecasting. And so weather forecasting in particular is a really interesting application for us as we're looking to build digital twins because, well, first, it's a great example of an unsolved problem where we don't know the exact equation governing the system. And it's an inherently multi-scale problem. So we need to look at different resolutions to resolve different things. And interestingly, climate and weather is currently limited by the available computational power. Simulating the entire planet for hundreds of years for several ensemble members typically is testing the limits of our best supercomputers. And so today we're only looking at about 25 kilometers, that's about 0.25 degrees. And if we want to be able to resolve accurately things like storm, we need to get to 1 kilometer. So even if the scale of compute continues the way it is, it will take us another decade to get there. And so the hope is that we can accelerate some of that with AI models. Another thing is that in many critical applications, like weather forecasting, we don't simply want a best guess prediction. what we want is to make informed decisions, and so we need to understand the range of possible outcomes and evaluate the probability of specific events. For example, if there's a hurricane, we want to know what is the probability of landfall in a particular area. And so that requires us reasoning about probability. And so this is typically done by running large ensembles. So we run many simulations with slightly perturbed initial conditions, and then we try to map out the space of possibilities. And so given that we're already limited by compute, this would be completely computationally untractable to do with existing methods. So that's why we'd want to accelerate them. And so that's where we're trying to bring in neural operators. So how do we do this on practice? Before I delve into the actual methods, I kind of wanted to map out the characteristics we would want out of a method to actually deal with these scientific problems. So the first one is, as I said, these systems are governed by equations, and the solution to those equations are functions. So we would want, instead of mapping between finite dimensional spaces, to map between function spaces. And to illustrate this, I think we're mostly familiar with neural networks that map from image to image, for example, or physics-informed neural networks are another example, where you learn a function of the coordinates and you try to map this coordinate, let's say x, y, z, to the solution at those particular coordinates. Instead, what we want to do is learn an operator that maps from any initial condition to the solution for those initial conditions. The second thing we want to do is we want to decouple resolution and number of parameters. So to do this, I want to just briefly use the example of like the perceptron of linear layer. Like, is everyone familiar with the linear layer perceptron? Okay, most people. Briefly, it's a very simple building block. It was the first practical learning neural network that was introduced, and it simply takes an input vector composed of a point f1 to fn here and maps them onto an output vector, also of fixed dimension, here g1 to gm. And the way it maps an input to an output, each output is simply a linear combination of the inputs. And the weights of this linear sum are learned end-to-end via gradient backpropagation, and they are given by this matrix K that contains all those weights. So then the problem is that we've now tied the number of parameters with the size of our inputs. If now we want to have the same function with more discretization points, you want to add more points to your input, you need to add new weights for those new inputs. And so the number of parameters will grow, typically quadratically or exponentially, with the input size. And so that means that if you want to study the same problem, let's say weather modeling, and go from 25 kilometers to 1 kilometer, it will quickly become computationally intractable. So we would want to decouple the two. And then once we've done this, it's kind of pointless if we can't actually use our model on different resolutions. So we would want a model that is resolution agnostic. So if you have an input function, you would want to be able to discretize it in different ways, feed it to your neural operator, and then have it output the solution for these initial conditions at different resolutions as well. And again, as a corollary of this property, you would also want something that we call discretization convergence, which simply means that you want things to stay coherent across resolutions. For example, if you're simulating the airflow around an airfoil, imagine you're looking at the same initial conditions, same airfoil, you give it different inputs, you would want outputs that are coherent. You don't want wildly different results at different resolutions. And so this essentially is what we mean by discretization convergence. It means that as you refine the mesh, you would hope that performance improves or at least doesn't get worse. So you can make use of higher frequency information, and you would want things to converge to a consistent limit upon the continuum. And lastly, as the speaker before me mentioned, there's a problem in a lot of those applications that we have limited amount of data. Unlike language, where we can have almost unlimited amount of data, even though we're actually reaching the limit of that, in science we often have very limited data sizes. And so we want something that is data efficient. And lastly, well, ideally we would want something that's well-founded. So for neural networks, we have this universal approximation theorem that tells us that it's basically an existence proof. It tells us that if you have enough capacity, so a network with enough layers and good properties like nonlinearities, enough channels, etc. For any continuous function, there exists a neural network that can approximate that function arbitrarily well. So that tells us, it doesn't tell us how to learn that neural network, but it tells us such a network exists. So at least what we're doing is not pointless. So these properties actually define the framework of neural operators. And so now I want to go over how to build them in practice. So first, I kind of want to introduce them from this linear layer that I already showed and show, for example, how you take this linear layer and make it into a neural operator. Okay, the order got messed up. Basically, in the existing case, and for linear layers, we were learning a function that was mapping between finite dimensional spaces. So it was mapping from an input vector to an output vector. Now we are learning an operator that maps functions to function spaces. And so instead of parameterizing our sum by a weight matrix, we now simply parameterize it by a function. And so now our output is a function of the coordinates, and once again, it integrates over the input domain with a learned kernel. So this is called the linear kernel integral transform, and it's really the foundational building block of neural operators. And so in practice, we approximate it with the sum version. And I want to quickly mention that there's a few important things to look at when you build neural operators is essentially looking at the continuum and making sure things stay consistent. So here, for example, you may have recognized the Riemannian sum approximation of the integral. And so this delta x is simply the quadrature, and it's there to make sure that as you refine your discretization, your integral will converge to the true integral. If you aggregate function values at irregular spaced points without this quadrature, the points that are more densely sampled will be accounted for more in the integral, and so different discretization will converge to different solutions, which we want to avoid. In the same way, if you look at the receptive field of your method, so for example, what neighborhood your method looks at, if you refine your discretization, you would want your method to take into account the same spatial domain. If you just look at neighbors, which a lot of methods in traditional deep learning do, as you increase the discretization, your receptive field collapses to a local one. And so you end up just doing pointwise operations. You end up using no context. So this is all just to say that one of the core aspects of building neural operators is looking at the continuum and making sure that things stay consistent across discretizations. And so the same way that neural networks stack learnable linear mappings, such as convolutions of fully connected layers or linear layers, followed by some normalization and nonlinearities, neural operators generalize these two functions. And so the general form of a neural operator is you take your input function, f of x, you apply some form of encoding that can be a lifting to higher dimensions to add more channels, for example, and then you add a bunch of those linear kernel integral transforms. Since they are linear, obviously you need to apply a nonlinearity afterwards, so you end up with something nonlinear at the end. You stack a bunch of those, and at the end you have a decoder that takes you back from your latent space to the physical space that you want to learn, and then you get your output function. So now we have this new powerful architecture, and so the question that we have to answer is, can we actually learn the operators we want to represent? And so this is what I mentioned earlier. We already have a universal approximation theorem for neural networks, and so luckily we also have one for neural operators. This was a result proven by my colleague Nikola Kovacsky when he was in Caltech, and it states that essentially for any input continuous operator, assuming a large enough model, we can build a neural operator that will approximate it arbitrarily well. So at least it is well-founded, and we have hopes. And we don't know whether we can learn it efficiently, but we know such an operator exists. So far, that was all quite theoretical. I told you about how to build a neural operator, what properties it has, and so now I want to show in practice on a few applications how you would implement it. So the first case is if you have your input is given on a regular grid, so a uniform discretization, and in that case, you could replace your general integral linear operator at the top by the special form of a global convolutional operator. So that's the Fourier neural operator that my colleague talked about in the talk just before. And the idea is that this can be realized very efficiently in the spectral domain. So the convolutional theorem tells you that doing this global convolution in the physical space is equivalent to doing an element-wise multiplication in the spectral domain. And since we have very efficient way to compute this Fourier transform, it's computationally very efficient. So what you do is you take your input function, you project it to a fixed basis space, in this case, Fourier basis functions. You keep a fixed number of these basis functions that is independent of your resolutions. For example, you could truncate out the high frequencies. And then you perform your element-wise multiplication and then invert the Fourier transform. And you learn the kernel directly in the spectral domain. So you wouldn't transform your kernel every time, you simply learn it directly in the spectral domain. So as I mentioned, you can do this Fourier transform in practice on discretized functions very efficiently using a fast Fourier transform, DFFT. That basically gives you an O of n log n instead of n squared, so it's much more efficient to do. And you simply would compose this global convolution with some nonlinearities. So you take your input, you apply your spectral convolution, apply a nonlinearity, and then notice the residual connection. As I think you mentioned earlier, FFT will just give you a periodic information as output. So you want the skip connection to recover non-periodic information and high-frequency information that you may have truncated out. So you stack a bunch of those layers, and that gives you the FNO, Fourier neural operator. And so one nice property is that now you can train on a given resolution. Here we train on a Navier-Stokes problem, so essentially a viscous fluid problem on a resolution of 64 by 64, and then we evaluated on unseen data at a larger resolution of 256 by 256. And the nice thing is if you look at the spectra on the right, you can see that our method in blue captured the energy spectra quite well, even on unseen frequencies. So it hadn't seen the higher frequencies during training, but then the spectra of the prediction actually matches. Well, if you take a neural network and you simply interpolate to make it fit the input resolution it expects, things get a bit nonsensical on unseen frequencies. So that was for uniform discretization. What if we have, for example, a sphere? And so what better sphere than basically Earth? And so in NVIDIA, we want to use machine learning to build weather and climate predictions and accelerate basically the process. So in 2022, we built the first version of ForecastNet, which is a reference to its origin with the Fourier neural operator. It's a data-driven model based on FNO to emulate global medium-range weather at 25 kilometers resolution. And it basically was able to predict 2 weeks of global weather in just a fraction of a second, which represented a huge speed up and also a huge energy saving. And it was able to stay stable, to do stable predictions across long horizons. So why is it important to actually take into account the fact that we're on the sphere? If you don't, on the left, it was a transformer-based architecture. Predictions are very good at the beginning, but if you unroll the model, so do autoregressive forecasting over longer horizons, things become nonsensical, while SFNO was able to predict reasonable outcomes for longer horizons because it knows things are happening on the sphere. So how did we do this in practice? Well, it's exactly what I presented before, except now we're on the sphere, not on the plane. So instead of taking basis function on the plane, which were sine and cosine, we now take circular functions, which are spherical harmonics. So the concept is exactly like before. You take your input, apply spherical harmonic transform, perform convolution in that space, and then invert the transform. And as I mentioned, we don't want just one best guess for the future state of weather. We need a way to generate large ensemble of possible futures to build a probabilistic distribution. And so this is a newer work. It's like, we call it ForecastNet v3. That was also led in NVIDIA by also my colleagues, Boris and Thorsten. And the idea is to make the prediction stochastic by injecting controlled randomness in the forecast at every step. And this is done by, in addition to taking your typical input variables, like your atmospheric state, surface variables, etc., you also add some noise. So we add some smooth random fields that cover the globe and that basically will steer the forecast into slightly different but still physically meaningful predictions. As I mentioned, it's the exact same framework as the FNO before. You take your input, apply either a spherical global convolution or a spherical local convolution. You can again see that we still recover our linear kernel integral. And then you can apply some pointwise operations and you stack a bunch of those layers and that gives you forecast nets. And so just to talk a little bit about training, since now we're not predicting just one prediction, we actually have an ensemble of predictions. So in this case, we train this with what is called the continuously ranked probability score, or CRPS, which basically will take a ground truth Y set of predictions by your model, these Xi, so these are your ensemble members. And the CRPS will basically minimize the average distance of each ensemble member to the ground truth, minus some penalty for being too spread, so for being too wide. And so we train the SFNO end-to-end via gradient backpropagation by minimizing a sum of the CRPS in the spectral domain and in the physical domain. And so this gives you well-calibrated predictions. And so the result is a model that outperforms traditional numerical weather predictions. And so on a single GPU, this should be an animation. Yeah. So on a single GPU, it was about 60 times faster than IFS, the integrated forecasting system, which is our gold standard. And it was about 8 times faster than GenCast. And so one nice thing is that now the model can directly give you ensembles, and each ensemble member is actually physical in the sense that if you look at its spectra, it has correct interchannel correlations and proper spectra. And so in turn, this is just an example. This is actually with an older version of ForecastNet. But if here we look at Hurricane Harvey in Houston, that was in 2017, and we're running several predictions with our model. And so each of those basically gives us one possible trajectory. And that allows us in turns to do probabilistic assessment of where the storm is actually likely to go. And what this means in practice is the more ensemble you have, the more accurately you can capture the whole distributions of possibilities. So if you only have 50 ensemble members, if your simulation is too slow and you can only get 50, you only get so many possible realization. And the more ensembles you can run, the better you can capture things, especially extreme events. So here, for example, extreme winds that are not captured by smaller ensembles. So essentially, by speeding up simulation, we can in turn get better probabilistic assessment of our risk. And so lastly, I just want to touch on arbitrary geometries, because so far we're on regular grids, either in the plane or on a sphere, but there are a bunch of problems where we have completely arbitrary geometries. One of those problems that we work a lot in NVIDIA is computational fluid dynamics, or CAR-CFD in this case, where you have an input geometry and you assume an inlet velocity and you want to see the effect of the flow around the car. So you want to measure surface car pressure and the drag. And so, yeah, sticking your car in a wind tunnel is obviously not an ideal way to do this. And numerical simulations can be quite slow, so we would like to speed up the process. And ideally, we would like to have a seamless end-to-end pipeline where designers can generate car geometries and immediately get feedback on what the drag would look like. And then once you have something that is reasonable, you can then do more accurate simulations if you need. And so one way to do this is the graph neural operator. And once again, we start with the same kernel linear integral, except now instead of integrating over the entire domain, which would be very costly, we can have millions of points, we are going to do a local integration over a ball centered on a query point. So the nice thing with GNO is that you can query it at any point. So now, unlike before, our input is a geometry. So we have a bunch of points, so a mesh that gives us the geometry of our car, and we want to predict what the surface pressure will be. So for each query point of your model, you find all the neighbors within an epsilon ball, and you basically aggregate information from all the points within that neighborhood. And so the GNO will basically stack a bunch of those layers like we did before until you get the solution. Or what you can do is now you can take a GNO, use it as an encoder to project from your arbitrary geometry into a regular grid. So you have your car geometry, you apply a graph neural operator, which you query on a regular grid. And now you can apply an FNO, which is computationally more efficient thanks to the n log n FFT. So you apply a bunch of FNO layers, and then at the end you can have another GNO layer to project back by querying on the points on the surface of the car. So essentially it gives you an architecture to project from an arbitrary geometry to a good, easy to work with latent representation where you can do your computation, and then you project it back to the desired geometry. And so in practice, we're able to get pretty good accuracies. And so this is a cost trade-off accuracy curve comparing the GNO, our methods, with OpenFOAM, which was run on, I think, a bunch of GPUs. I don't remember how many. But basically, you can get, for similar accuracies, you can get much faster simulation time with these methods. So obviously, you could get better accuracy with a solver, but it would take you a lot longer. So actually here you can see we're about 10,000 times faster than a numerical solver. And so finally, I know like a lot of you work on actual physical problems where you do know the equations. And so in that case, if you do know the PDE governing the system, you can use it as a loss. So you first would have your data-driven learning phase, where you compare the prediction from your model with the ground truth, backpropagate, and learn the model end-to-end. And then, given a new instance, you can take the predictions, the output of your model, plug them into the actual equations, and use this error as a loss to fine-tune your model. And so that allows you to do instance-wise fine-tuning. And so if we look at the same problem as before, if you remember, there was a bit of a mismatch still between the spectra of our prediction and the ground truth. If we do this instance-wise fine-tuning, you can see that the spectra of the ground truth and of the prediction match almost exactly. So this is an easy way to then incorporate physics within our model. And so finally, I just want to touch a little bit about scaling. As you're all aware, we completely changed regime. There was a lot of time where we had, curse of dimensionality. We thought that if you have too much data, it would be very hard to learn something sensible. But lately, it seems that the scaling laws actually tell us that the more compute you have, the bigger your data set and the more parameters you have, the better performance you get. So this was from the famous paper Scaling Laws for Neural Language Models. This was for LLMs in the context of language. But it applies much more generally to a lot of applications. And one of the challenges in scientific AI is that the routines we need are not always available. And so in a lot of cases, we need to write custom kernels. For example, for the spherical harmonics for ForecastNet that I presented before, there was no existing implementation that was efficient in PyTorch. So our initial implementation was way too slow to train anything. So then Triton gave us some speed up, but that was still way too slow to train. And so we wrote some custom kernels that actually allowed us to get good iteration time and actually train the models. So custom CUDA kernels allow you to speed up computation significantly, and so train things a lot faster. The other thing is data and model parallelism. If you need to scale the model, you at some point reach the point where you cannot fit your entire data in the GPU. And so what you can do in this case, you can distribute your data across multiple devices. And then if that's still not enough, you can split your model, which is what we did for ForecastNet, onto multiple devices. So then each GPU or each computational device will get part of the input, perform its computation, and everything is then synchronized. So essentially, you trade memory for communications between the devices. And two other techniques that are very useful for neural operators are incremental training. Now we have a model that is independent of resolution, so you can do most of your training at low resolution and fine-tune on a few high-resolution instances to speed up training. And you can apply techniques like tensor factorization, either to the parameters or to the gradients, to significantly reduce the memory footprint. So these basically give you ways to speed up training, scale up the models, and reduce the memory footprint. And so the last thing I want to say is how to train those models in practice. I think one really nice thing about the field is that we had a lot of open source science, and that actually made a lot of the recent discoveries possible. And so we tried to also keep all our science open. So Torch Harmonics, which has those custom kernels I mentioned, is fully open source. You can directly plug it in your applications to use spherical harmonics. We have open sourced Makani, which is the entire training framework for ForecastNet. And we have an open source library called Neural Operator, which basically aims to make all those neural operators available directly in PyTorch. So now you can import any of the models, for example, the FNO I just talked about, or the SFNO, GNO, etc., and simply use it as instead of any other deep neural network model, and use it to train on your applications. So then everything is resolution invariant, and you get all the properties of neural operators. So it's fully open source, and we also have a series of products where key technologies are regularly ported, and those are very mature framework, tested, and they scale really well. So if you have concrete applications where you need this kind of reliability, we have those products. So to conclude, neural operators are basically a rigorous framework for scientific computing in all cases where you need things to stay consistent across discretization and capture multi-scale phenomenon. So I hope this gave you a good overview of what's possible. There are many other types of neural operators. We're working, for example, on foundation neural operators, versions of transformers that have this discretization invariance properties, etc. So I think, yeah, there's lots of really exciting works coming up in this space. So I want to thank all the many colleagues and collaborators that contributed to these works. This was really a big team effort, and I want to thank you all for listening.
Great. So next we have Fredrik Lindsten from not as far away, Etienne, so from Linköping.
Okay, did I have a clicker here somewhere as well? Makes it much easier if I can also change slides. So. Okay. Thank you very much for the introduction. My name is Fredrik Lindsten, and I will talk about training-free guidance for generative models using Bayesian inference. So generative models have revolutionized machine learning and AI in recent years, and we've seen very impressive results when it comes to things like synthetic image generation. But the same models can also be used for many applications in science. One example is to generate plausible protein structures conditionally on an amino acid sequence. And another example that we heard about in the previous talk, and that we'll also hear much more about tomorrow, is in weather forecasting, where we can use generative models to generate hypothetical or sort of plausible future weather states for probabilistic forecasting. So in these examples, these examples make use of what I refer to as flow-based generative models, which essentially means that we want to approximate some complicated unknown data distribution, p data here, with some generative model, p theta. So this is an approximate probability distribution. But this model p theta is defined implicitly through a sampling procedure. So this can, for instance, be based on stochastic differential equations, so SDs, which is referred to as diffusion models, in which we then generate the sample x from this p theta of x by initializing a stochastic process by sampling from some simple distribution, typically a high-dimensional standard Gaussian, and then we run some stochastic process through some artificial time, and then we take the final state of this stochastic process as a sample from p theta. If we repeat this multiple times, we get multiple independent draws from our sampling distribution. The theta here refers to parameters of some neural network that kind of underlies this stochastic process, defines the drift in the stochastic process. But for the purpose of this presentation, we don't have to worry so much about that. I will assume that we have access to a pre-trained such generative process. So this is sort of SDE-based, a stochastic process-based formulation. There's also one based on ordinary differential equations, in which case we have sort of the stochasticity in the sampling process comes only from the initial condition. So again, we sample some latent variable Z here from a standard Gaussian, and then we run an ODE initialized at this point through some artificial time, and take this output or the solution of this ODE as our sample from p theta. And in this case, we have sort of a sample x here can be expressed as a deterministic function t theta of the initial condition Z. And this function then is simply the solution map to the ODE. Right. In many applications, however, we are not only interested in sampling from some data distribution that we learn, but rather to sample from a conditional distribution, so some p of x given y, where y is now some auxiliary information. It could be, for instance, some property that we want to condition on if we want to work with, say, drug discovery and want to find molecules with a particular property, or it could be some partial observations that inform us about the state x, such as, or for instance, in the context of data simulation for weather forecasting. Now, one approach to tackle this problem would be to try to learn this conditional distribution directly from pairs of x's and y's, so paired training data. But that is not always possible or desirable. So instead, we might look for sort of training-free methods for doing this conditioning, in the sense that we assume that we have access to a pre-trained model for sampling from the unconditional p of x, and then I want to in some way modify that sampling procedure so that I can sample from the conditional p of x given y. So as an example of this, we can consider the problem of image completion or image inpainting. So assume that we have access to a generative model that can generate pictures of faces. And then I want to sort of use this model for completing this picture. I give it the left half and I want it to fill in the right half. But there are many possible ways of doing this image completion. So we still want to have access to a probabilistic model that can generate many sort of possible solutions. But we don't want to train sort of an explicit sort of right half image inpainting model. Instead, we want to use our pre-trained model that can simulate or generate full images. So one way to kind of address this problem is as Bayesian inference. So this means that we view our generative model, p theta of x, as a prior in a Bayesian inference setting, meaning that we now define some likelihood term, p of y given x, which tells us how this kind of conditioning argument or auxiliary information depends on the state x. And then through Bayes' rule, we can now express this conditional distribution p of x given y of interest using the prior and the likelihood. So for instance, in the image completion example, we could simply assume that this likelihood term is some Gaussian observations of the left half of the image with some small added noise. So it's a simple likelihood function, but then we combine this with a complicated prior that comes from our generative model. Right, so essentially we can view this as a standard Bayesian inference problem and throw any approximate inference method on it. But at the same time, we know that there is a lot of structure in our generative model. So then we can ask, can we use that structure in some way to improve the performance of our inference method? And I will now show you two examples of this that we have been working on. So the first one we call flow ESS. And this is joint work with Etienne Kalaivanan, who is sitting somewhere over there. So you can talk to either him or me if you find this interesting in the break. And also Shang Shao and Jens Sjölund. So this method applies to this ODE formulation of the generative model, in which case we have this situation where we map sort of a Gaussian, like high-dimensional Gaussian latent variable Z to our samples x through this ODE, and that is defining a deterministic mapping T. And we now want to combine that with this Bayesian inference formulation, where the generative model here now implicitly defines the prior P of x. Now, expressing this prior is kind of complicated, but what we can do instead is to simply make a change of variables. So we express our posterior of interest in the latent space. So try to find the posterior of Z given Y instead. And doing that, we now obtain a, sort of a formulation here where we have a very simple, just standard Gaussian prior, and the complexity in the generative model has been moved into the likelihood term. So we're working with a formulation with a high-dimensional Gaussian prior and complicated likelihood, and then you can kind of make use of your favorite MCMC method for this. And one of my favorite ones, which suits this problem formulation, is referred to as elliptical slice sampling. So what that means is that if we consider this situation now with, again, we have the prior P of X, and we combine that with some likelihood that I've illustrated in this orange, with these orange level curves here. The posterior would essentially be, well, roughly speaking, the intersection between these curves. Now, as I said, we want to apply this MCMC method in the latent space. So since it is an MCMC method, we are working iteratively and generating samples. And at each iteration of the algorithm, we have access to sort of a current state, which I denote by this, show here by this red cross. We're working in the latent space, but each point there also corresponds to a point in the target space. Right, so to move from this point to sort of a new point, the new state of the MCMC chain, we first simulate one point from the prior in the latent space, and this will again map to some point from the prior in the target space. We then connect these 2 points with an ellipse, which is centered on the origin, and this ellipse will kind of trace a curve in the target space as well. And then we can essentially just do a one-dimensional search along this ellipse to try to find a point which has high likelihood. And that will then become the next state of the MCMC chain. So the benefit with this method is that it only requires point evaluations of the generative model itself, no gradients, so meaning that we don't have to backpropagate through the ODE solver that defines this mapping T, nor any density values for P of X. Sort of a limitation here is that being gradient free, it struggles when the support of the posterior becomes too concentrated compared to the support of the prior, which is a situation we end up in if we have very informative observations. But we have applied this to some problems where it seems to work very well. So here's one example from material science. We took an off-the-shelf flow-based generative model called FlowMM. Was published at ICML last year. And then we said, okay, take this off-the-shelf method and then condition this on particular properties. And I show here, sorry for the small fonts here, but show here 2 rows with 2 different properties. On the top row, we have, we say that we want to generate materials with a particular value for the shear modulus of 200 gigapascals. And we can then see that the proposed method here, which is, should point here maybe, proposed method, which is here to the right, seems to actually respect that constraint sort of fairly well. And the other 3 here are other sort of conditional generation models that have been proposed. Same at the bottom, but there we instead condition on an energy above Hull, which is negative. So we're essentially just searching for stable materials, you could say. Okay, I said that I wanted to show 2 examples of this. So the second example is a method called decoupled denoising sequential Monte Carlo. So this is joint work with PhD student Philip Ekström Calvinius and also Sheng Zhao. And this was published at ICML this year. So you can read more in this paper if you're interested as well. Right, so this is an alternative approach for kind of tackling the same problem, which instead tries to make use of the sequential nature of the generative process. And in this method, we assume that we have a linear and Gaussian likelihood term. So that's kind of a limitation, although this still captures many sort of interesting problems. So the way this method works, I'll try to illustrate here, and this slide probably makes most sense if you know something about how diffusion models actually work, so apologies if you don't. But again, we have this situation where we kind of map standard Gaussian that we have over here to some data distribution using a generative procedure. And it's quite common in the diffusion model literature to view this kind of generative process going backward in time. So that's why I've showed it in this way. So if I draw a sample here from this Gaussian and I map that through my generative model, I end up with this x hat 0 over here, which is a sample from the prior. But again, we want to combine this prior with some likelihood term, resulting in sort of posterior distribution here instead. So in order to accomplish this, we can imagine that we take our sample x0 and place like a Gaussian bump around that point. And we then view this blue curve here as a prior distribution in the target space. And since this prior is now by definition Gaussian and the likelihood is also linear and Gaussian, we can work out the sort of approximate posterior that comes from this, which is the purple curve here. And this will be a rather poor approximation of the actual posterior, but we have still kind of nudged our samples in the direction of the likelihood tells us. So what we then do is that we sample from this approximate posterior and then propagate that sample forward in time, but we don't go all the way to the end, but we stop at some sort of intermediate time step. Then we can repeat this procedure. So from here again, we reconstruct a kind of a clean sample, we place a small Gaussian bump around that, and the variance of this Gaussian is decreased as we come closer and closer to time 0. And then we repeat this procedure. So this sampling procedure here is quite similar to another method that has recently been proposed, which is called decoupled annealing posterior sampling, or DAPS for short. It was published at CVPR this year. We do something very similar, so highly inspired by DAPS. It's slightly different, but the main difference sort of is that we then place this within a sequential Monte Carlo framework. I won't go into the details of that, but essentially it allows us to kind of compensate for the approximation errors that we get through this Gaussian approximation that we introduced. And for those of you who are familiar with SMC, what I showed on the previous slide, that defines actually the proposal distribution for SMC. So as a small proof of concept here, we have applied this to a toy model where we have a target distribution that we can actually sample from. So it's an 800-dimensional Gaussian mixture model. And I've just projected it here onto 2 dimensions for visualization. So the prior here has 25 components, but then the likelihood is such that only 3 or maybe 4 of those components have non-negligible probability mass. And we have the proposed method over here and compare it to some other methods that have also been proposed for solving this conditional sampling problem. And we can see that it, in this case, seems to do a good job in kind of avoiding to sample from these spurious prior modes that have no probability mass in the posterior. Okay, so in summary, diffusion models and flow-based models can learn complex distributions from data, and they have applications in a wide range of scientific fields. And conditional generation can enable us to kind of steer these generative procedures to target or specific target properties or condition on observed data. And viewing this conditional generation as Bayesian inference allows us to make use of our Bayesian inference toolbox with methods such as MCMC and SMC and other approximate inference methods to obtain this kind of training-free guidance. Okay, thank you very much for listening.
Hello everyone. So yes, I'm Etienne Russeil, a postdoc working here at Stockholm University, and I'm working on supernovae science. But also in parallel, I've been very interested in symbolic regression. And in particular, we've developed in the past years methods that we call multi-view symbolic regression, and that I'm going to talk to you about today, what it is and how it's very interesting and relevant in many different sciences. So first, I want to talk a bit about my background and why I got interested in this subject. So what I do is that I look at supernovae. Supernovae is the explosion, very extreme explosion of stars at the end of their life. And typically, if you would look at the sky and take multiple images with a telescope of the same region of the sky, sometimes you see a very bright dot appearing, getting brighter and brighter, and then fading before it never appears again. And one thing you can do to study them is to actually draw this, what we call light curve, which is the evolution of the brightness of your star as a function of time. And what you would see is this exponential increase in brightness followed by this decay. One of the ways that we actually make sense of these light curves is by modeling them. So there are many ways to make sense of light curves, but when you are dealing with a very large amount of data, which is the case of these newer telescopes, which will produce millions of alerts per night, you would like to have fast methods to actually process this data. And so what you can do is do something very simple. You choose a parametric model, which is purely phenomenological in the sense that you describe the data, but not really the physics behind it. And you fit your model, and the parameters that you obtain with this fit are kind of summarizing your data. So on the top, I show what is called the Bazin model. It's a super classical model to fit supernovae light curves, which are not weird. And it has been widely used by the community because it's simple. It describes this exponential rise and this exponential decay. And when I arrived in my PhD a few years ago, I was kind of puzzled because I didn't really understand which model I should use to describe my supernovae, because in the literature, many different persons propose many different models with more or less complexity, capable of fitting with more or less precision, with more or less parameters, etc., etc. And so I was wondering which one I should use. And yeah, also there are many different types of supernovae, so which one I should use for which supernovae? It was a kind of mess. And naturally, I started investigating this field of machine learning that is called, no, wait, wrong order. If I summarize my problem, this looks something like this. I have a supernova mechanism, which is the physics behind it that generate the explosion and the very complex physics happening here. And because of different initial conditions in the explosion, the progenitor star, and because of many observational effects, is the star far or not, is there dust in between us, etc., it will generate many different light curves from the same type of mechanism. And my goal was to find the best phenomenological model to fit all these light curves generated by the same physics. But this model is not necessarily physical, it's purely descriptive. And when you think about it, this is a super normal problem. This has nothing special for supernovae science. Like I could completely remove supernovae, and in the context of any science, you have a given phenomenon, and given some experimental setup, you generate a bunch of observation of the same physical thing, and you want, again, to find a phenomenological model to describe this observation in kind of a precise way. And now, to answer this question, I started learning about symbolic regression. So it's a kind of a growing field, but it's not very big yet. So as a kind of summary, symbolic regression is this machine learning field where you try to find the best equation that fits your data sets given the raw data. So, for example, here you have this super complicated data set. It's a line that was generated by the 2x plus 3 function. And ideally, purely from this data, you would like to recover this 2x plus 3. And the core idea in most of the symbolic regression implementations today is that it uses what we call genetic programming. So it kind of mimics the Darwinian evolution to converge and explore the parameter space of possible solution in an efficient way. So a few months ago, I made some outreach talk where I designed this little equation as being individuals from this Darwinian evolution. So I keep them. So what we start by doing is that we first randomly generate a bunch of solutions. and this solution will typically be pretty bad at fitting your data because they were random. But they will not be all equally bad. Some will be worse than others. And so what you would do is that in the same fashion as evolution, you would select your fittest individuals. So the one which has the poorest fit in the metric that you want, you remove, and you keep the ones which are a little bit better. And then similarly to the DNA, you will apply some random mutations and hope that your best individual with some random mutation might create individuals which are a little bit better. And so you do this, you randomly mutate, 3x becomes 3x squared, etc. Obviously, there are not 4 individuals, but probably 100 or thousands. And then what you do is that you repeat this again and again and again, and you will slowly converge towards better and better solutions. And so ideally, after many generations, you get your perfect individual, and you've successfully fitted a line, and you're very happy. But you've done more than fitting a line. You actually understood that a line is the best fit for this data. It's slightly more complicated. But okay, this is great, and this is symbolic regression as it's most commonly done. But the point is that my problem is not exactly this. My problem is that I have many lines. And what I want to understand is the parametric model, AX plus B, in the sense that A and B are parameters. This is what I want to recover. I don't want a particular fit to a particular data set. This is just not enough. And given this setup, current symbolic regression was not able to answer this question. And so we started working in developing what we called multi-view symbolic regression. The idea is that it's almost exactly the same, except that now individuals, the equations that we manipulate are directly parametric models. And so for example, here I have an individual AX squared with A being a parameter. And what I do is that I minimize A on each of my example that I give as an input, so on each of these lines, to get the optimized A value that gives the lowest loss. So I get an array of losses, so here, for example, mean square error loss. And then somehow I aggregate these losses into a single one that will represent the score of my single individual. So I could, for example, take the average or the maximum loss, or different strategies could apply here. And in the end, if you do this and you do exactly the same with the mutations and the selection, you will end up directly with a parametric model that is able to properly represent all of your examples at the same time. So this was done a few years ago. It was published 2024, but we actually showcased that this technique works, that it works better than using single examples to do the same thing. And very interestingly, what I wanted to do is to try it on actual scientific data. And so first, obviously, I applied it on my supernovae because this was my PhD thesis. So yeah, inputting a bunch of good quality light curves into my algorithm, I obtained some very interesting results. The first one that actually was remarkable is that we could reconstruct this Bayesian model I was talking at the beginning that is very widely used purely from this data set. So we use this data, put it, try to fine-tune a little bit the hyperparameters, and this is what comes out, and it was actually very impressive for us. And we also generated a lot of various models depending on a little bit how we adjust the hyperparameters. Some are original, some are better, some are dubious. But this one I like particularly because you can see the fit is overall better, and it requires one less parameter than the Bayesian model, but it has a super weird exponential of exponential form that is absolutely not intuitive to anyone, and that usually people look at me weirdly when I show them. But it works very well, and this is actually one of the interesting things, is that you go beyond human intuition when you build your model, because the Bayesian model, for example, is just someone that said, okay, it's exponentially rising and decreasing, I build my model so that it does exactly this. Okay, we also went on a kind of quest to apply this idea to other science fields, so For example, we went to see the chemist in my old university and asked them if it was any useful to them. And maybe you recall, or if there are chemists in the room, there is this super basic Beer's law, which describes the absorption of a solution as a function of the concentration. And usually what chemists say is that it's linear until 1. And if you go above, you don't talk about it. And so we tried to actually concentrate more and see, and found with just one extra parameter that we can describe pretty well the full behavior for a range of different molecules. And we also went to talk to economy people and try to apply this again, and it was kind of interesting results. And in fact, while we are doing this, very remarkably, this idea appears under different names and with different groups multiple times. So somehow this year was the year that it should have been discovered. So we used Operon for our first test, and the result I just showed you, it's an implementation of symbolic regression that we kind of upgraded for this. There is another implementation called PhiSO, which is a group that exactly at the same time published basically the same idea. And then a bit later you have PySR that maybe some people know, it's quite famous in physics, that again upgraded to kind of perform this multi-view approach. And recently we developed this PyEcPy implementation that I will make some advertisement for in a second. So hopefully today, but it's not there yet, so maybe tomorrow on Archive we published a new analysis for this, where we actually again explore many different data sets. We try a bit all these implementations, try to understand what it brings on the table, what should be improved, etc., etc. So stay tuned if you're interested. Now in this paper, just to illustrate a little bit, we use a galaxy rotation data set. We use this Nicorazze data set, which is a fluid mechanic data set. We use biology with enzyme conversion, etc., etc. So we actually try to really showcase that this tool is kind of accessible for all kind of sciences purposes. By the way, here I show only kind of two-dimensional examples, but this can work in n dimension. Okay. Now, if some of you are actually interested in using this thing, I would recommend using our latest thing. It's called EcPy. The idea is that it's based on the so-called equality graphs. So inside, the equations are represented as graph, but there is this kind of modern version of graph, which are equality graph, meaning that's two equations which are mathematically the same. For example, x plus x or 2x are usually two separate things that you need to explore twice. But with this equality graph, you actually merge them into a single graph, which is smartly designed, that you would avoid exploring the same equation multiple times because it's just written in a different way. So it actually improves quite a lot the research speed, and this features the multi-view approach that we use. It is quite fast. It's among the fastest method that we tried, and it provides quite good performances. And recently we actually added a Python wrapper so that it's very easily usable with just a pip install EcPy. Okay, so just to illustrate a bit that it's not that much of a big deal to use, there is a kind of tutorial notebook available on the GitHub, and it goes like this. So here I generate super simple data set for the example. It's just 3 views generated from a polynomial function with some Gaussian noise. So it just looks like this. And this is not EcPy, it's purely the generation of the data. And what you can see, and that is very interesting, is here I specify the parameters from the views. And in each of the views that I use, there is one parameter that is set to 0. Meaning that it actually really showcases the power of this method, because every single view alone is not enough to recover the full functional form, because okay, one of them will just be a plus bx, and so the square part you will miss, etc., etc. And there, by actually combining all the examples at once, you can regenerate the full functional form at the beginning. So yes, only 3 examples, very simple. And so what it looks like is quite easy. You have a kind of scikit-learn format. You just create your regressor, and you do a .fit MVSR on your data sets that you give, which are just lists, and it works. Here, I will show hyperparameters in a second, but just to showcase, this is what the results look like. It's not actually a single solution, because what is the best model is very dependent on your own definition, and especially the best model is always a trade-off between simplicity and accuracy of the fit. So obviously you could get an infinitely precise model with a size equation like this and a polynomial of degree 54, but probably this is not what you want. And so the results are actually given in the form of a Pareto front, which shows the best model at each level of complexity. So you can actually decide which model is good enough. So yes, you have here the literal expression fitted on each of the views. So the 3 first line are for the 3 first views for the first expression. You have a NumPy version of the expression so that you can actually use it very quickly, and this is very handy. You have the values of the parameters that were minimized for this specific view. The size of your model, so you see increasingly big, size 1, 3, 5, 7. And then you have the loss on each function and the aggregated loss overall from the solution. Here, obviously, the example I show is extremely simple, so I don't even need to tweak the hyperparameters, but depending on your problem, you might want to change this. Especially, you can include or exclude any operators that you want from this research. So if you say you work with supernovae and you think that an exponential is a good idea to describe your curve, you would include the exponential. But if you work with something that doesn't look exponential at all, you can remove it. And similarly with, I don't know, log, sine, cosine, and kind of a big list of operators that you can use. You can also select a kind of maximum size from your equation in order, if you know that you want a simple model, you don't want to waste some time in exploring an unwanted thing. And you can also set a maximum number of parameters, because let's say, I don't know, the current state of the art is 2 parameters and you wouldn't go beyond 4 or something like this. And so here, if I show a little bit this Pareto front illustrating, you can see that so this is solution number 0, 1, 2, etc. And you see that you quickly see that as you go more complex, your loss drops. Solution 4 actually has a loss very close to 0. And as you increase, it doesn't really seem to improve that much. But the number of parameters keep increasing and the equation size keep increasing. So probably solution 4 is the one you would like to go with. And obviously, because I planned this, it is actually the correct solution, but I did not fine-tune anything. So you actually recover the full model, ax plus b plus c squared. You feed them, it works, and you see that you have your correct Pareto front. So again, this example is available if you want to try very quickly and try on your own data set. So to conclude, this multi-view symbolic regression is a kind of new method that expands the classical symbolic regression and kind of puts it to real condition for actual scientists, because for a long time symbolic regression was handled by computer scientists that wanted most accuracy within as much as possible as much precision as possible, independently of whether the model makes sense or not. So this actually improves a lot the interpretability of the model that you generate. It has shown many good results over many different data sets, but okay, it's very young. It has 2 or 3 years now, so the field is moving very quickly. New implementation arrives, change, improve. So I think there is a good future for this, and I encourage you to try it by yourself, even if you don't try ECPI or just one of the current ones. Thank you.
Welcome to the afternoon session. We will continue with the theme that was started already before lunch, namely application of AI to mainly astrophysics and cosmology. And our first speaker is Luisa Lucie-Smith. Welcome, please.
Okay, hi everyone. I'm Luisa Lucie-Smith. I'm a junior professor in machine learning for astrophysics at the University of Hamburg, and I want to thank the organizers for inviting me here. It's a really exciting workshop to be at, and I want to tell you a little bit about the work we've been doing on trying to develop explainable deep learning models in the context of astrophysics and cosmology. So as I said, I'm a cosmologist, I'm a theoretical cosmologist, and our goal is really to try to answer fundamental physics questions about our universe. So things like how did the universe evolve, what are we made of, and how did all the structures that we see today come about. And so essentially what we're trying to do is that we're trying to sort of reconstruct a timeline of the universe, starting from sort of the initial Big Bang and the formation of the first stars that we think happened around 400 million years after the Big Bang, to the formation of the first galaxies and planets and all the large-scale structure that we observe today. And so I don't think I can really stress enough how exciting it is to be working in the field of astrophysics and in particular large-scale structure like right now. And this is because we will have basically orders of magnitude increase in our data over the next decade. And this is because surveys like galaxy surveys like the Dark Energy Spectroscopic Instrument or Euclid or Vera Rubin LSST will basically complement each other in area, in depth, and in resolution, giving us basically beautiful pictures of the universe, a large-scale structure, and detailed features of galaxies, like in these pictures here. And so to be able to really fully exploit this data to answer those fundamental physics questions, we really need essentially robust cosmological models that can be compared to this very precise data. And so just like in particle physics, there's a standard model of particle physics, we also have that in cosmology. And basically our standard model, although it's been actually phenomenologically very successful at describing a large variety of data that we have available, actually still rests on ingredients that we don't understand their nature at all. And these are, for example, dark energy, that is a form of energy that we introduced in our cosmological models to explain the present-day accelerated expansion of the universe. We have dark matter that I'm sure most people here have heard of, which is basically a form of matter that dominates the matter content in the universe, and basically without it, we wouldn't even be able to explain the formation of galaxies, yet alone their properties at all. And then we have inflation, that it is another paradigm that we have to introduce to sort of explain the origin of the tiny inhomogeneities that then grew under the action of gravity in all the large-scale structure that we see. And so this is basically what motivates us to analyze our data and compare it to our theoretical models to really try to pin down the nature of these still unknown ingredients in our standard cosmological models. And so what do we do essentially? And you know, astrophysics or cosmology is quite a unique science in the sense that we only have one universe, right? So from observations of our single universe, so pictures of, for example, that's a map of the cosmic microwave background, so sort of a picture of the universe, what it looked like at very early times, together with many different probes of the later time universe. We want to do the inverse problem. So from the data, try to infer back properties about those fundamental ingredients in our models. And typically, we describe our cosmological models in the form of a few parameters, actually only 6 cosmological parameters can describe the large variety of data that we have available. So as cosmologists, our daily job is that, essentially trying in many different ways to do this inverse problem from the data, inferring back the cosmological parameters that from which the data comes from. And so what is the difficult part in doing this? One of our major theoretical challenges is that most of the predictions of our models now tend to rely on very computationally expensive and highly nonlinear models. And so I just wanted to show you here an example of a cosmological simulation, which is basically our best way or our most accurate way to describe this evolution of the universe that I was telling you we want to try to reconstruct. Following essentially the evolution of the dark matter as well as the gas and the stellar components throughout cosmic time. And so what you see here, essentially, for example, in the middle panel, is kind of gravity at action, right? So at the beginning, you have only small inhomogeneities in your matter field, but things that were slightly overdense at early times grow more and more overdense over time. And so you start forming these highly overdense regions that we call dark matter halos. And the gas and the stars tend to sort of follow this skeleton large-scale structure that is really dominated by the dark matter. And so you see, for example, on the left, you have the gas, and in the right panel, you have the stars. And so you see, for example, that the galaxies, so the stellar components, tend to form at the center of these overdense regions of dark matter. And so running this cosmological simulations, especially if you want a big volume that can describe well the statistics of the universe, but also getting it to be able to describe the details of the galaxy formation, so at pretty high resolution, is a very, very computationally expensive exercise to do. So simulations that are really state-of-the-art like this ones, we only really have a few available because they can take months or more to run. And so, where does AI come in? And for us, AI has really played a central role in addressing some of these theoretical challenges. So the fact that we would otherwise be really stuck with this computationally expensive and highly, highly nonlinear gravitational processes. So one place where AI has, I would say, at least in astrophysics nowadays, really taken over kind of a part of our inference pipelines is in the field of accelerating these computationally expensive models. So this is similar to what we're hearing about in the first talk today, of building sort of surrogate models that can sort of replace the known models that we have and just making it faster. So just accelerating these computationally expensive models. And this is just one example of these surrogate models from the CosmoPower emulator, where essentially the typical idea is that you use as input those cosmological parameters, and you want to predict with a neural network the cosmological observable. So instead of having to run your full simulation to get the predicted cosmological observable for your given input cosmology, you just have this fast surrogate model that, okay, given this set of cosmological parameters, what would be for example, the power spectrum of the cosmic microwave background fluctuations, or what would be the distribution of galaxies? So cosmological observables that we then compare to the data. And this doesn't just allow you to sort of accelerate computationally expensive models, but it also allows you to use new cosmological observables that we wouldn't be able to use otherwise. Because now the neural network basically is a model that gives us a prediction for, say, for example, you applied it to properties of the emptiest regions of the universe called voids, for which otherwise we would have no other model other than these emulator neural networks. So another application that in the cosmology community people have been trying to push forward is essentially the ability of AI, of machine learning, to extract non-Gaussian, so very complex patterns in the data. So as you saw from that cosmological simulation, essentially the large-scale structure, so the final galaxy distribution, is a result of very highly complex nonlinear gravitational interaction. So most of the information, a lot of the information about the cosmology lies actually in these non-Gaussian, nonlinear scales. And so people have been trying to basically use machine learning, for example, convolutional neural networks, to try to extract non-Gaussian summary statistics, going beyond what we can do with our traditional statistical models, for example, using the power spectrum, which we know can only describe, is only complete for purely Gaussian fields. And so at least in simulations, so in pretty controlled training scenarios, we see that indeed deep learning has the potential of extracting that additional information on the non-Gaussian nonlinear scales that would otherwise be lost when using only the power spectrum. And so you can see this in this right panel here, which is the typical parameter constraints that we look at in cosmology, where essentially you're looking at basically the regions of parameter space that are constrained by the data. So if you only use the power spectrum, you have broader uncertainties because you're using less information about that initial field. But if you extract some summary statistics from using deep learning, you can use additional information in that input and get tighter constraints on cosmological parameters. And this, in principle, can really revolutionize cosmology, because the tighter you get these cosmological parameter constraints, the more you can distinguish between different cosmological models that might describe dark energy in different ways or dark matter in different ways. So let me just take this one as sort of a case study where I think that machine learning's potential and applicability is actually limited by its sort of black box nature. So we see in many studies like this one that deep learning definitely has some potential. As I just described, it definitely has the potential of extracting more information than what we could with traditional statistical models. But then the question is, okay, where is that additional information coming from? Which aspects of the galaxy distribution or the galaxy property is the CNN or whatever deep learning models you're using extracting in order to say something about the cosmology? And so, we have, at least in our community, endless discussions about, would we be able to claim, a discovery? So, for example, say I tell you with a deep learning model something about the nature of dark energy or something about neutrino masses, if we cannot explain how that discovery actually came about. And typically the answer is no, right? People agree that if I give you a result and I cannot tell you how I got there and you have no way of verifying the robustness or the validity of that claim, you would not trust it. And so I think this is where, at least to me, explainable AI really comes in. I think as physicists, we are not satisfied with models that we do not understand. And so I think we should try to build models that try to follow at least some of the standards of good physical models. Not all physical models are good, but at least the good ones that we hope our models have. And these include robustness, an explicit domain of validity, generalizability as well, and of course, understanding in its broader definition. But at the same time, of course, in order to exploit the power of AI and that potential that we see in many different applications, we also at the same time have to try to retain those characteristics of deep learning, right? That allow us to go beyond those traditional statistical techniques. And that, to me, are the ability, for example, to build very flexible models that are highly complex, that can work well in high-dimensional spaces and can learn these sort of non-linear patterns, which are certainly very relevant for astrophysics and cosmology. And so I see, explainable AI essentially as an umbrella which kind of bridges between physical understanding and AI in the black box form that we're used to dealing with. Okay, so what do I mean by explainable AI? And again, there are endless definitions and discussions in the community, in the different communities actually. But at least to me, there are sort of two requirements for building an explainable AI model. So one of them is interpretability. So this means essentially accounting for why the machine learning model reaches a certain prediction. So in some way is saying, okay, given some machine learning model, can I read off in some way, even if approximately, what that function is? And so it could be, for example, going into a layer of your network and saying, okay, this layer is learning this sort of pattern, or this kind of input that has more importance in giving me the correct answer versus this other part of the input. But this is not really enough. So interpretability alone is not really enough, and you always need a second aspect, which is that of explainability. So this is basically the ability to map that understanding onto the relevant science domain. So in other words, it's something like, okay, given some machine learning model, can I associate the learned parameters or some function of that parameters to the domain knowledge? And so, if I have the interpretability part, so I can say, okay, look, this layer is learning this sort of pattern in the data, but I can't explain what that pattern means in terms of the physics that I'm interested in, then that's not really helpful. And we are just writing a review and actually having a lot of fun in discussing these kinds of concepts and definitions with Recap Gambir and Jesse Thaler as part of a FISTAT initiative, so stay tuned for when that will come out fairly soon. Okay, so what is the issue with interpretability? I mean, I'm sure most people that work on AI know this. There's this sort of trade-off between interpretability and expressivity, at least we call it expressivity. Which essentially means that, okay, you can go to the most interpretable model that there is, something like linear regression or just a simple decision tree, and then you can really understand, right, how the input is affecting your output, or what that function is, or how your input space has been partitioned. But of course, you're stuck with just a simple linear relationship or just a simple binary partition. Or you can say, well, I want to go all the way to the most predictive, most expressive models, those that kind of do the feature extraction by themselves, so in the sort of deep learning regimes, but that of course comes at the cost of typically millions of parameters, or sometimes less as well, which is why there's these so-called black box models. And I just want to make the point, going back to the astrophysics aspect of this, that explainability is actually, at least in my view, not just an issue in machine learning. It's actually an issue in many of the models that we use in astrophysics or cosmology. So most of the time when we analyze those complex simulations that I was showing you at the beginning, we can't actually understand, the macro physics, like how did a galaxy form in that way? Why do some galaxies have certain shapes? Why do they stop forming stars? Why do they continue to form stars? So we can model the microphysics of it, so just the gravity, but we don't really have a macro physical understanding of galaxy formation or halo formation. And so what we end up doing is that we just have some empirical fitting functions that we try to calibrate their parameters to the simulations, but we also don't understand, we can't really derive them from first principles. So I would say that explainability is actually an issue for most of the modeling that we do in the context of large-scale structure, actually, even for basic and fundamental ingredients of basically all our cosmological analyses, which are things like how do halos and galaxies cluster relative to the underlying matter, how many halos or how many galaxies do I have of a given mass, or how is matter distributed within and around a halo, so their density profiles. And so I think that explainable AI, is not just a method to gain trust and understanding of your results, but it's actually an opportunity, at least for large-scale structure, to actually learn about something new, about these emergent properties that we see in simulations and of course, in our data as well. Okay, I don't know, 5 years ago or 4 years ago, I was very inspired by this paper that came out that was talking about how would one design, deep learning models for this idea of knowledge extraction. And so they started thinking about, okay, well, how do humans learn, right? So you have a bunch of data, and what you typically want to do is that you want to compress that data into some simple representation, so that if you ask me a question about that system, all I need is really the information that is encoded in that representation to give you an answer. So for example, imagine you have some particle trajectories. Well, they made a very simple example saying, well, to predict the position at a later time, t prime, so if I ask you, where will that position be at a future time t prime, all you need is just to the initial position and velocity to give you an answer for that query. And so essentially they translated this idea into a neural network architecture, where this time you have the data, and then you have a neural network that compresses that data into this low dimensional latent representation, and then given a query, I can give you an answer based just on the information that is in that latent representation. So they applied this to pretty simple 1D problems, and they basically found that the latent parameters that they would that the network would discover would align quite well with the physical parameters that they were expecting from this simple 1D problems. And so essentially what we wanted to do is to apply a similar idea to one of our cosmological problems. And the first case study that we use is basically in the context of modeling the density profiles of dark matter halos. And again, for the non-experts, this is basically a major ingredient in all cosmological analysis, in astrophysics, in cosmology, and even in particle physics for some of the direct and indirect searches of dark matter. And again, we have these kind of fitting functions that work in certain regimes, but we were in particular interested in these regions sort of outside the halo boundary that carry interesting cosmological signatures and that deviate, at least what we see in simulations, deviate quite strongly from the assumed typical fitting functions. And so what we wanted to answer is essentially, can neural networks discover the building blocks of these halo density profiles out to this regime where we don't have a good empirical fitting function from simulations. And so the idea is that, okay, you have as input, let's say the raw data, so the 3D raw data from your cosmological simulation. And you have an encoder that does the compression step. So you're trying to compress all the information that is in this 3D raw data into a simple, low-dimensional latent representation, so that when I want to predict the density rho at a given R, all I have to do is use the, can you see my mouse? No. All I have to do is use the information in that low-dimensional latent representation. So in some way is similar to a variational autoencoder, but it's not an autoencoder. So you're not trying to compress all the information that is in your input to reconstruct the input entirely. You're only trying to retain the information that is relevant to predict rho as a function of R. And so here, the encoder in this case was a 3D CNN, because we deal with 3D boxes from our convolution, from our cosmological simulation, and the decoder was just a simple feed-forward neural network because we're just interested in predicting rho as a function of R. Okay, so you know, essentially, at least for me, the key property that this latent representation has to have in order to be interpretable is disentanglement. So what this means is that you're trying to build essentially independent factors of variation in your output to be captured by different independent latents. So again, kind of drawing similarities from variational autoencoders, the simplest thing you can assume is that you can describe this latent representation and a set of independent Gaussians. And so what the encoder is really doing is that it's predicting the mean and the standard deviation of each of these latents, which you can then sample to get different realizations for your density profile. And so this disentanglement is encouraged via the loss function that is optimized during training. So again, very similar to the beta VAE, to the beta variational autoencoders. You have one term that is sort of your log likelihood. So trying to get you basically predicted density profiles that are as close as possible as the truth. That is weighted against the KL divergence term that basically tries to push the learned latent representation to be as close as possible to this prior that you've imposed of independent unit Gaussians. And so the way we actually measure the level of disentanglement between the different latents is via mutual information, which is actually a very standard metric in information theory, just however quite tricky to estimate. And we spend quite a lot of time coming up with a new estimator for mutual information based on Gaussian mixture model, which is actually publicly available if you're interested in using it. Okay, so once you have this latent representation, you've trained it to give you good predictions for the profiles, but also to try to generate this low-dimensional latent representation that describes sort of the independent degrees of freedom in your problem. How do you actually interpret this latent representation? And as I mentioned, we really use mutual information as the main metric for explainability, so for relating that latent space back to the domain knowledge. And so what you see here is basically the mutual information between each latent. So in the left panel, if you assume a two-dimensional latent space, it's the mutual information between the latent and the density profiles. And you see, okay, there's one latent that has information about the profile on some radial scales up to this R200, which is basically the boundary of our galaxy or of our halo. And then you have a second latent parameter that basically has no information about what's happening in the inner density structure of these galaxies, and then lots of information in the outer region. Then if you include a third latent parameter, you see, okay, I need a third parameter to give me some extra information around this halo boundary region, and then a fourth latent parameter basically has no information about the profiles. So this already tells you about the dimensionality of your problem. So you need 3 independent degrees of freedom, in this case in the form of these latent parameters, to describe these density profiles out to this radial range. I'm going to speed up a little bit because I'm a bit behind. But so you can do then many things with this latent space. So now you've basically generated not only a model that can give you good predictions for the profile, but also the 3 independent degrees of freedom in your final output. So you can actually, systematically vary one of them to see what happens in the profile, and you very quickly see, okay, one of them is actually just a normalization. The other is sort of the outer slope, and the third one is some sort of inner slope parameter. And then you can say, well, okay, what can I do with this latent space beyond its original training task? So another, I think, requirement of good physical models is generalizability. So does this latent space actually retain any information on, for example, the origin of halo density structures? And so what we did here was, again, using mutual information to try to see whether these independent latent parameters could be related to the physics that gave origin to these halo density profiles. And so what you're seeing here is basically the mutual information between the 2 shape latents and the evolution history of the halo. So you see, okay, the yellow one, which is the inner shape, has information about sort of the buildup of the halo at early times up until a certain time or redshift, and then it doesn't really care about what happens to the halo at later times. Whereas the outer shape one doesn't really care about how that halo formed. It could have formed in a more overdense region, in a more isolated region. It doesn't really care about how it built up its mass at early times, but then becomes very sensitive to the late time accretion rate of the halo. And so this is just to say that, although we only trained it to learn about the density structure of the galaxies, we were actually able to relate these latents to the halo evolution history, learning something new about how these outer profile depends on only one component that is related to the most recent accretion rate of these galaxies. And so we basically applied this sort of network, which we call the interpretable variational encoder, to different aspects of astrophysics and of cosmologies, where we could essentially basically get some new sort of physical insights into these emergent properties of the logical structure that I was describing to you at the beginning. And another thing that we've been thinking regarding basically these neural-based model compression is, okay, well, we've applied them to sort of improve some of the modeling that we're doing in astrophysics and in cosmology. But let's forget about the theory for a second and think just about the data. So can we actually use this neural-based model compression techniques to try to discover and constrain what are the most important degrees of freedom in the data directly? And this is basically motivated, again, by the fact that some of the recent analyses of data from galaxy surveys have pointed towards certain tensions in our cosmological parameters when using different data sets. And so what we wanted to know is, okay, which what are the independent degrees of freedom in our data, and which parameters does our data really constrain, to try to figure out where could these tension possibly come from. And so we started, basically from the simplest or most well understood cosmological probe that we have, and this is the power spectrum of the temperature fluctuations in the cosmic microwave background. It doesn't really matter. I guess most people won't know what that means. But it's a very well-established cosmological probe, which we could guess, I guess, is what some of the independent degrees of freedom would be. And we wanted to see whether the neural network could actually recover these. And so in this context, we actually used a variational order encoder, not the kind of supervised version that I showed you before, to sort of fully reconstruct the entire cosmological probe at hand. So again, here we basically wanted to take the actual data vector itself and see, can we reparameterize it using these sort of model compression techniques to give us basically what are the independent degrees of freedom that are constrained by the data. And so we did this in the context of a cosmological model that is fairly interesting to explain one of these tensions. Again, for the non-experts, this doesn't really matter, but it has this exotic component of beyond the standard model called early dark energy. So it's a form of dark energy that was present at early times. And we wanted to see essentially if we could encode all the cosmological information in this low dimensional latent representation. And so I'll spare you all the detail, but essentially the most interesting thing we found that was previously unknown with the standard sort of techniques to do parameter inference is that we could actually isolate the information in this exotic early dark energy component into one latent. So we were able to actually, discover one single degree of freedom that is sensitive only to early dark energy effects and not to all the other standard cosmological parameters. So in some way, some form of smoking gun signature of this early dark energy effect in this particular cosmological probe. So in addition to quantifying that information in the latent space, we can actually use it also to constrain it with the data, just like we do for our cosmological parameters. This time we use the latent spaces and constrain it against the data from Planck, looking again at the constraints for, in particular, that latent that we know encodes only early dark energy effects. So here we weren't actually able to distinguish between the two theory models, because as you see, the purple contour, which is that from the data, is too large compared to the differences between the theory model. And this was actually expected, because we know that from this data alone, it's impossible to actually distinguish between these two models. But the goal is now to add more cosmological probes and see whether we can find signatures of these tensions in latent space, and then relating them to the actual scales in the data vector themselves that these latents encode. So I think I'm running out of time, but yes. So let me just end here saying that, we're now sort of in the new era of much bigger models, foundation models, also self-supervised contrastive models, where you typically have much higher dimensional latent spaces than the ones I've showed you here. And so we're basically working on seeing how disentanglement scales for these kinds of much bigger models, what kind of different interpretability tools we can use. Do we need to include new structures in the latent space, including hierarchical dependencies and causal dependencies? And so I'll leave it with sort of these challenges in case there is some nice synergy maybe between people of different fields that may be interested in similar questions. Let me just leave it here, and thanks a lot for listening.
So I will continue the story of our universe. I will talk about mostly what we are trying to do for square kilometer array observatory, which is being built and which will be the largest radio telescope of the world. And for this, with this telescope, it will be a frontier of data-driven science, because it will produce petabytes of data per day, and we will need AI tools to extract meaningful information or physics from this data. So let me start with this beautiful image of the night sky. So right now the night sky is full of stars and galaxies, but there was a time when everything was dark. The universe was completely dark, and my job is to be a cosmic archaeologist and try to dig into this excavation site of the sky and try to find a lost civilization of the first generation of stars and galaxies in the universe. This is what we are trying to do with, we're planning to do with the SK observatory. And this period of our universe, when this first stars and galaxies form, is also known as the cosmic dawn. So the dawn, time when these form. So this, we have a tool to do this, which is the telescopes, or the SK telescope, which can help us in doing travel back in time because of the finite speed of light. So if we look farther back, farther objects, we're looking at as it was in farther back in time. For example, if you look at the sun right now, it shows us how it was 8 minutes ago, and so on. We can look farther and farther stars and look back in time. Liz already showed you this baby picture of our universe, which is the cosmic microwave background radiation. I'll quickly just comment on this, that this shows us that the universe was started off from a distribution of matter which was almost random. Not many any structure during this time, and also during this time there were no stars and galaxies. And then the universe evolved to this current picture, which where we can see more structures. We can see web-like structures. That's why it's called the cosmic web. And all the stars and galaxies are embedded in these bright spots that we can see where these webs connect. And what we're trying to do in my work is to try to find this time between this period when the universe was almost random to a very structured universe, and this time is an unsolved mystery, because we have no we have almost no information about exactly when this cosmic dawn happened and how it happened, and what were the physics that that drove the processes during this time. So we can think of it as a cosmic, here be dragons of cosmology. We're starting to see something about this era with the James Webb Space Telescope. Here is a first deep field image with the James Webb Space Telescope. So here are some of the candidates which could belong to this cosmic dawn period. This image is very with the James Webb Space Telescope. It's difficult to get a full picture of the cosmological structures that should be there during this cosmic dawn. So in this left image here, I show you a simulation of how structures should look like during cosmic dawn. During cosmic dawn also we expect there to be web-like structures, and then this is a simulation showing a size which we need to statistically learn something about cosmology of during this cosmic dawn. But the images that JWST is producing is about 100 times smaller than this big picture that we want to see. So we have another tool to observe this era, which is the 21 centimeter signal. So this is a special signal which is produced by neutral hydrogen, and this is called 21 centimeter because it has a rest frame wavelength of 21 centimeter. And if we try to look at this same universe using the 21 centimeter signal, it will look something like this. So we can see again the intensity of this signal is nicely following the structures in the left side. So the left side is the matter distribution, and the right side is the 20th centimeter signal. But in this image on the right, I have assumed that there is no stars and galaxies formed. So if and the universe is completely neutral, and the 21 centimeter signal is produced from neutral hydrogen, neutral gas. But when the stars and galaxies form, they will ionize the gas, emit photons, and they will ionize the gas around them, and they'll start to form these blue dark patches in this map of 21 centimeter signal. And these patches are very interesting and very informative because they will tell us that there is stars and galaxies forming in the universe. Even if they're very faint for JWST to see it, it will form large structures which can be measured with the 21 centimeter signal. And as 21 centimeter signal is a line, by observing this signal at different wavelengths, we can reconstruct the evolution of this era. So we can observe different times. We can observe it at the age when it was 700 million years. We can observe it later at 800 million years. And by observing it at different times, we can look at this evolution of these dark blue patches. And from that, we can see how the population of these early stars and galaxies evolved and developed, and how they're clustered in the universe. So for this, we are building the square kilometer array telescope, which will be very large, and it will be sensitive enough to detect this signal. But just measuring the signal is not enough. There are other challenges that comes with it. There are many sources of contamination in the signal. Here on the left now, I show you what we expect from the initial data, SK data, which will be very noisy, but still we want to do something with this initial data. If we smooth it down, it will we can see that the large scale structures in the clean map and this degraded noisy map matches. So there is some information, but by smoothing it down, we are losing some of the interesting small scale information present in this data. So maybe with the traditional methods, it might not be optimal to extract physics. Therefore, we are looking into developing AI tools to try to optimally extract information from these noisy data. And luckily, this year, very recently, this year, the SKO office organized a data challenge for all the groups across the world to compare, validate, test their AI tools to extract information from the initial SK data. So what they gave us is that they produced a model of, they created a model of the cosmic dawn, and they added all the contaminants, and then they picked up chunks from this simulated model, and then corresponding to different frequencies or different cosmic times. They gave us 3 cosmic times, and then the goal was to determine the ionization fraction of the universe. So the idea was to calculate what is the fraction of these blue patches in the images that I showed you earlier. Here on the right, I'm showing you neutral fraction, which is simply 1 minus the ionization fraction of the universe. So this was the goal, and we took up this challenge as a team called Search, which was a collaboration of data scientists and astrophysicists from here in Sweden and also Switzerland. And for this, we developed and tested several methods, which is listed here. I'll not go through all of them. What we did is that after developing them, we wanted to find out which one we should use in this data challenge. So we did our own internal data challenge and found out 2 methods which were winners for us, and then we applied this to the SK data challenge. I'll go through these 2 methods, which we call traditional and modern. Even though one of them is called traditional, it is not less sophisticated than its modern counterpart. So first, the traditional method, which also could be called the seasoned expert, which is constituted from the Bayesian inference framework. We have seen this equation multiple times today. We want to determine the neutral fraction of the universe, which is theta, the parameter, given the data. So the noisy SK data or mock SK data that SK of SKOs. And this would depend on the likelihood function and the prior. Just to quickly, I will say about this framework, I'll use this simple example where we have a projectile being thrown from this point onto the wall, and we have information about data about the position of the where it's hitting the wall, which is the red point there, and the idea is to find the most likely path. And if we know have a functional form for this likelihood term, then we can evaluate the value of this likelihood for all the paths, and then find out which is the most likely path, and that's the most likely path value of theta. But sometimes this problem is not so simple, and there could be some sources of contamination or some physics that are very difficult to model. For example, if there are gusts of winds, random winds going on, so the projectile, the path of the projectile can change. So in those cases, what we do is we can do something called a simulation-based inference, where we create thousands of models, and then we find out patterns between the data, simulated data, and the model parameters. And then from that, we can approximately learn something about the posterior distribution, and then evaluate for our data. So this is the first method that we applied on the SK data, which is simulation-based inference, where we start from the 3 data set or 3 images that SKO gave us, and we used a compressor to compress the data into a latent space, which here I'll mark as summary statistic. And for this compression, we'll need a loss function, and for us also as Luisa explained, a very good loss function was to find out to use the mutual information. So we compress the data to a latent space which maximize the mutual information between the latent space values and the neutral fraction in our models. And after that, we learned the posterior distribution of our training set, and then we applied this to the SK data. And this is the result that that we got. So here I'm showing you the 2D posterior distribution for 3 different frequency bins, and how they are correlated with the other frequency bins. The take-home message from this plot is that our answer are those colored contours, which is showing the sigma contours, and the black dashed box is the region defined by SKO, which is allowed by and where we should be to get the correct answer. And the cross is the center of this box. And you can see that we are not exactly at the center of this box, but our most probable region is mostly inside this box. Now moving on to the modern method, what we call the modern method, but we can also call it a creative learner, because in this case, what we did is that we tried to learn patterns in the images that we have in our training set. So we wanted what we used for this is we used something MLP mixture network, and in this network we have multiple layers. Each layer has 2 components. One is token mixing. What this token mixing does is that it divides up these images into small patches called tokens, and what it does, it learns the common patterns between these patches. And there is another step which is channel mixing, where it tries to find more accurate features inside each of these patches, each of these tokens. And then after learning these patterns, it finds a model that's mapped to the neutral fraction in our training set. And once we have learned trained this network, we applied it on the SK data, and this is what we submitted for the data challenge. Again, we see some sort of bias in our constraint parameters, but still it's somewhat inside this black dashed box. But the more important thing is to see how we did compared to other teams in the world. So there were 30 teams about 30 or maybe more than 30 teams who participated in this challenge, and both our methods came out to be third and fourth in this challenge, which is very good. We found that our tools can be applied to the real data, and then we expect the answer that we get is somewhat close to the true answer. The data challenge also had another provided another data which was much more challenging than the previous one. In this case, the data also contains something called the foreground signal. So here again, I have the low resolution version of the noisy data that I showed you earlier, and here is a realization model of the foreground that is expected to be there in these 21 centimeter signal. And what you can think of foreground as something like we are trying to look for stars in the daylight. So sunlight will be with this foreground signal, which will wash out the entire sky, and we won't be able to see any star in the daylight. And in this challenge, we were supposed to find this signal from this where there is foreground. But for this, we had a special framework which we call SereNet. This is a UNet architecture which is trained to clean foreground signal from this data. So we start from images of the 21 centimeter signal containing this foreground, which is several order of magnitude more intense than the signal, and the output is the 21 centimeter signal. And we tested this network on our training set, and it worked quite well on our training set. We also added another extra feature in this unit. So this is a normal unit, but in this unit we added another feature where we can add any prior knowledge about the field that we're observing into this network. So here visually we have shown this binary prior as the prior knowledge. So if we know for the same field of field, if we know the distribution of galaxies, then we can provide that information into this unit, which can be used to better subtract this foreground from the 21 centimeter signal. And applying this method to remove foreground signal, and then we applied our two methods to extract physics from the data. And this is what we finally got. So here I am now showing you the 1D posterior distribution instead of 2D distribution, because very few teams could take up this challenge. Only 4 submissions, only 3 teams, because 2 of them are from one team. And here in this posterior distribution, you can see all the submissions that were done by all the teams. For this we did quite well, but we struggled a bit for these higher frequency channels. And we are trying to improve on this method and trying to find, with SKO, we're trying to find ways to improve our network, improve SereNet, so that it can work better for SK data. But what does this mean? Why do we do this data challenge? And the true reason for doing this data challenge and why it's very important is that we have no prior map of the 21 centimeter signal from this cosmic dawn. So we are completely blind to what we would get from SK. And that's why this data challenge is the first step to know and calibrate our methods to be able to work on this data, this kind of data. And now after this challenge, we have created a bridge to be able to apply this finally to the initial SK data and be able to extract some physics from this initial data. And the two very massive challenges that we found from all this work is that we need two things. We need very good tools to remove contaminations from the data. So one of the things that we have developed is Serenet to remove foreground. There are other sources of contaminants which was there, and we still have to work on them. The other thing is to convert this data, this noisy data, into physics, and for that we develop these two methods, this SBI method and the other MLP mixture method. But we still have to improve a lot more to better extract physics from this data, because this is a very difficult, noisy, contaminated data set. And then we, like I said, the SK will produce huge amount of data every day, petabytes of data every day. So these automated methods are very important to be able to find useful data in the data sets and single them out so that we can do further physics from this data. Okay. That's
Thank
it.
you.
Okay, perfect. So hello everyone, my name is Ludvig. I'm a PhD student here at Stockholm University, and it's my pleasure to be here today to talk about one of our recent projects on learning the universe by learning to optimize cosmic initial conditions with non-differentiable simulators. So I decided today to divide this talk into 3 different parts, where we will first of all have a look at why we need non-differentiable models, given the data that is now being collected, as Luisa already talked about. I then will talk about why cosmic and cosmological initial conditions are important and a very rigorous test of the cosmological model. And then I will end the talk by mentioning the method that we have developed, the learning the universe by learning to optimize algorithm and leveraging neural networks. So let us jump straight into the next generation data, or maybe we should now start to call it current generation data, because it's actually being collected as we speak. So as is the case with many other science fields, cosmology is becoming a data-driven science. So I here have a figure showing you the number of galaxies that have been observed as a function of the year, either photometrically or spectroscopically, which are 2 different ways of observing galaxies. You see here an exponential growth in the number of galaxies that we have observed over the last couple of decades. And we're now reaching billions of galaxies with these new surveys, such as Euclid and the Vera Rubin Observatory. In the blue bar there, you see some approximation to what we would call like an upper limit to the number of galaxies we will ever be able to observe in the observable universe. This is extrapolating the Hubble ultra-deep field, which is a very high exposure, long exposure image of a small region of the sky, and then extrapolated to the entire night sky. The method that I will talk about today is something called field level analysis, and I will introduce it directly after this slide. It's currently analyzing roughly hundreds of thousands to millions of galaxies as of today. But we will have to scale this up to incorporate all these billions of galaxies that will be observed over the couple of years. This is a very challenging problem because it transitions into a model challenge where we have to include both small-scale physics in very large cosmological volumes at the same time. So the method that I will be introducing is the so-called field level analysis, which is an optimal way to extract cosmological information from our surveys. And to truly test cosmology, we need to fit our state-of-the-art models to the limits and see where they fail. And this is something that is enabled by field level analysis, where we can basically probe all the nonlinear smallest scales without any compression and doing, for example, the power spectrum analysis, as Luisa talked about, which would be at the population level. What we want to do and try to do with the current analysis at the field level is you have your cosmological initial conditions, basically how the universe looked like in the very early phase around the time of the cosmic microwave background. is evolved into the galaxies that we can observe today. And we can discretize that into a 3D grid, and we can try to fit object by object instead of on the population level. So instead of saying we have this amount of galaxy clusters, for example, of a particular mass, we want to fit them one by one, every single one. So what is currently done is to include so-called approximate structure formation models, both to generate the so-called dark matter underlying density field, which you then also can populate with the actual tracers, which is the galaxies themselves, which send out light, with some kind of approximate galaxy bias model. I will come back to why this is done, but that's basically because you have a requirement on the differentiable aspect. Now, what we have introduced with this work is basically a framework to incorporate the most sophisticated state-of-the-art models for simulating the universe into this kind of field level analysis, where we can now include so-called numerical n-body simulation codes, which are non-differentiable, and halo finders, HODs, hydrodynamical codes into this framework, which are also non-differentiable. But before I talk about that, let me just tell you what the cosmic initial conditions are and why they are a very rigorous test of cosmology if we have access to them. So what I mean by the cosmic initial conditions, as I already alluded to, is basically this box which contains, it's actually a Gaussian field that encompasses or encodes the density perturbations of the early universe. They are the seeds that then give rise, after the course of gravitational collapse over roughly 13.8 billion years, the so-called large-scale structure of galaxies that we observe today. And to show you this more visually, this is a very nice visualization that Stuart McAlpine in our group here in Stockholm have been running. And you will see here a simulation which has actually been constrained by real galaxy data. This means that the structures that you see here are constrained by data and corresponds to real structures in our actual observable universe. So you see here also, as have now been discussed over the last two talks as well, you see these filamentary structures. You see the high density regions in yellow, and that's basically where it's most likely that we form galaxies that then can trace this underlying dark matter density field. But in order to create such a simulation, a computer representation of our actual universe, we need to have access to the cosmological initial conditions. So instead of going the way of just simulating, what my work is including is doing this inverse problem of inferring what kind of initial conditions could have given rise to the large-scale structure that we observe today. So this essentially can be done in multiple ways, but we want to find the so-called posterior distribution. That's the set of all possible ways that you could have constructed this large-scale structure field of today from some initial conditions. So in this framework, as I already mentioned, we make use of numerical simulations to basically map from a given structure formation model or cosmological model M, with some specific cosmological parameters, omega, we want to find the initial conditions, x, that give rise to the observable 3D distribution of galaxies of today that we can observe. So this includes having some kind of prior model of how we think the initial conditions should look like, sending them through your favorite structure formation model to, in the end, with some galaxy bias model, end up with the galaxies that we see today. This framework, which is the current best one on the market, is the so-called Bayesian origin reconstruction from galaxies, the Borg algorithm, does this in a very high dimensional space of inferring every single voxel in your 3D grid. So that's roughly millions of dimensions that you need to simultaneously infer. And in order to have this update step of how to better match your data, you need to differentiate through this forward model. And this is similar to backpropagation in neural networks. We need a differential model in order to go from your data space back to how the early universe looked like and how to better update them to match your observations. But we don't only want to find one estimate on how the universe looked like. We want the so-called set of possible initial conditions that could have given rise. So this is a very heavy statistical machinery of inferring those initial conditions. So lastly, before I go into the actual method that I've been developing, let me just tell you why these cosmic initial conditions, when we have access to them, is a very rigorous test of cosmology. So you can imagine, if we have access to the initial conditions, you can simulate the entire structure formation, the dynamical evolution of our universe. And you can make use of data sets to cross-correlate, to learn about physics, to constrain cosmological parameters. And we also get, as it says here, the full formation history of both densities and velocities in the universe. So this term has already been mentioned a few times in different scientific fields, but basically what we're creating is a cosmic twin or a cosmic digital twin of the universe, where basically all the structures that we observe we want to fit in our model. And this is a very rigorous test because we basically need to simultaneously fit all the observed structures. Here is one recent work by our group where in the top figure you see the simulation output from inferred initial conditions using this method that I talked about. And then in the bottom, you see a compilation of roughly 100,000 galaxies, where every single red dot is a galaxy. And you see here in the zoomed-in region that we fit very nicely the underlying structure in our simulation as compared to the data. We can go beyond this and not only look at these, if we can fit the so-called large-scale structure, but can we fit the intricate properties of individual clusters that we observe. We can also check for how many of certain mass clusters that we observe in our simulation output as compared with real data. This includes, for example, anomalous superstructures that have been arising question in the communities, for example, the Great Wall, Giant Arc, and so on. Other things, as I mentioned, we get access to the velocities. These could be useful and have been shown recently to, through field level analysis, give you a lot of insights into the velocities of the universe that could be useful, for example, for tackling the challenges of inferring the expansion rate or the Hubble constant of the universe. And more specifically, if we zoom in, we can even have a look at the specific formation history of our galaxy and our galaxy pair Andromeda. So this is another work that was done by a collaborator of mine where you basically see the Milky Way and Andromeda pair forming and all possible ways that this galaxy pair could have been formed. So having access to the initial conditions basically gave us access to do a lot of different tests, and we need to fit them all at the same time. Otherwise, that could indicate that there is something that needs to be updated in our cosmological model. So in order to make use of the data that is now being collected, what I've been pushing is basically to do this field level analysis in less computational time and at higher accuracy as compared to state-of-the-art field level inference works. So I've been pushing two different frontiers in terms of leveraging neural networks. And I will talk briefly about the first one, but then more focus on the second approach. But we've already heard about surrogate models or emulators as a way of using neural networks to speed up your simulation. That is the first approach that I've also been pushing. And the second approach, which I will go into more detail, is the so-called search engine way, where we have a neural optimizer that basically searches for possible initial conditions. And that comes with some other benefits that I will talk about. But just to start off with, this field level emulator we have developed in order to speed up the simulation itself. So in the same kind of schematic as I showed you previously, works exactly the same, but apart from having this approximate simulator that has been used in the past because you need a differentiable model, we now put a so-called VNet neural network model into this framework that makes you simulate your universe to a percent level accuracy as compared to state-of-the-art numerical simulations, while also improving the speed by a factor of 100. So this kind of inference that we did here could not have been done. If you would have used a full n-body simulation, just computationally wise, it would have taken something like 40 years to conclude this kind of analysis, because you need to run this simulation many, many times to find the set of initial conditions that could have given rise to the observed structure. Now, we did still ask the question, what could we have been doing if we wanted to incorporate these state-of-the-art simulations directly that can model all these complex dynamical behavior at the smallest nonlinear scales? So this is why we introduced the learning the universe by learning to optimize algorithm, or in short, LULO, where we use a neural optimizer to not speed up the simulation itself, but to speed up the inference or optimization process instead. So here in this left box, you basically see the physics simulator pipeline, where we have input and output pairs. Now, the output of that physics simulation can be compared to data, which could be real observations, or as we did in this work to demonstrate the method, could just be mock data generated by a simulator. We then give this so-called data discrepancy to your neural network, which has been trained to map the discrepancy in data space to an update step in your initial conditions. This process is then iterated over, where you update your initial conditions, run a new simulation, compare the output of that simulation with your data, and then your network is producing the update step in the initial conditions such that next time you run the simulation, you better match the data. So this comes with some benefits as compared to having a field-level emulator, which is basically that we move out the machine learning modeling from the physics into the search engine. And some of these concepts now that I would like you to take with you from this talk is basically that we push a way of using a neural network as an optimizer instead of a predictor. And this enables to keep a full physics simulation in the loop without having any requirements on the having a differentiable model that can back propagate through. So this allows for now non-differentiable components in the state-of-the-art simulations. That is typically the case. So just to give you an idea of how we train this model, I want to just show you how this neural network architecture looks like. The UNet model was briefly mentioned in another talk previously. Here we use the so-called VNet model, also working on different hierarchies of scales, which has been shown for the hierarchical structure formation to work to be very compatible, since this also gets or extracts information and models that on different scales. Now, in this particular work, we use the so-called dark matter halo field and also a mass-weighted halo field where we can take into account the masses of these dark matter halos to a different degree as data input. So basically, given those data discrepancy vectors, we want to predict how to update the initial conditions of the simulator. For those of you that are interested in actually how we train this, we used a cosine similarity loss. This is a very high-dimensional problem. We're using a dimension of 128 cube, which corresponds to the number of pixels or voxels in our field, and we need to search that space. So that's a very high-dimensional problem. So we went for a cosine similarity loss since it gives you the direction to move in, as compared to, for example, a mean squared error loss, which didn't work as well for giving you the direction that you need to update in this high-dimensional space. And you might also ask then, how do we actually train such a model? We do this by taking some initial conditions and running them through a structure formation model, an n-body simulation, and then putting on top a so-called halo finder, which is non-differentiable, that groups particles together. We then do a perturbation on this set of initial conditions while keeping the same statistics. So we keep the same mean and variance of this initial conditions field, but we do a perturbation to it. Then we run that simulation forward and get some new output in your data space. Then we collect these pairs where we have the the discrepancy in the initial conditions space, and we have the data discrepancy. And we collect these pairs, and in this particular work, we used 5,000 pairs, which seemed to be enough when we did some studies on this. And then we used that basically to train the model on how to update initial conditions to better match your data. So let me show you some results of how this actually worked in practice. To the left, you see a slice of this 3D field. This is the dark matter halos gridded to 128 cube grid cells. And then to your right, you will see the reconstruction. So what's happening under the hood here is we get new initial conditions and we pipe them forward in your simulator, and then this is the output then that we can compare with the true data. So you see here as I play this video that in the beginning, the structures don't really match that well, but as we run further along, basically what the neural optimizer is doing is now zooming in and updating smaller and smaller scales to basically now have a very nice agreement between the inferred initial conditions that are then forward simulated with the ground truth. So just to show you how this looks like in different kind of fields that we get access to, or data quantities, in the top panels you see the true fields, and in the bottom fields you see the reconstructed fields after 22 optimization steps, which corresponds to 96 simulations that we ran. So you see to the left the initial conditions that were reconstructed. You then see the halo reconstruction as we saw on the previous slide to the right. And then in the middle here, we get a byproduct, or byproducts. We get the underlying dark matter density field that was not used as data to construct the initial conditions. And we also get access to the velocity field. This is basically because we have two ends here that we need to fit simultaneously. We have some kind of boundary conditions on the initial conditions. We know how they are supposed to look like, more or less. And we need to fit the data of today. Since we have then this deterministic mapping between these two ends, we get all these other byproducts for free, essentially. And they match fairly nicely as well. So with that, oh yes, right, I just highlighted a few of these regions where we actually do fit to a very high degree as with the true data. Brings me to my summaries. So basically, next generation galaxy clustering surveys are here right now. And our capability to analyze this nonlinear data at nonlinear scales will basically limit our knowledge gains. So the approach that I have been pushing and that I introduced to you here today is the inference technology at the field level, since it offers information optimality by fitting object by object in our surveys. We get a complete characterization of cosmic structure without any compression, since we make use of full nonlinear structure formation models in the framework, and the entire model and inference is at the field level at all times. So in the end, this makes a very rigorous test of the cosmological model if we can simultaneously fit all these structures. And the two approaches that I've been mentioning in terms of AI and deep learning is the neural model, which increases the efficiency of the simulation itself, or the neural optimizer, which provides now a non-differentiable or gradient-free framework to incorporate these non-differentiable simulators. And all in all, that gives us a very promising path forward towards analyzing current generation galaxy surveys at nonlinear scales. Thank you.
So please, Laurence, take it away.
All right, thank you so much. Thanks a lot for having me. This has really been a lot of fun, so I'm super happy to be here and to be discussing about a lot of cool science with machine learning. So I'm going to be talking about some recent work that I've been doing in the space of like high-dimensional inverse problems. And so I'm going to start the talk by just saying a bit like the same thing that like the previous three speakers have been saying about the fact that we live in this really special time in astrophysics and cosmology where there's a new generation of sky surveys and observatory that are starting to take data. And so we're about to get completely flooded by a huge amount of new data. So that's sort of the usual narrative in the machine learning and astrophysics talk where you say, okay, huge amounts of data coming, we need machine learning because we just cannot cope with like the sheer volume of things. But I want to take sort of a different aspect and say there's another aspect of this data that's really important, and that it's complexity. And so the point is that like with every new generation of telescope that's coming online, the complexity of the data is increasing. So much so that like our current analysis methods are just not sufficient to capture all of the information that's like in that data. So what I mean by this is that when the data is simple, then like simple analytical models with a handful of parameters are enough to capture all the information that's in the data. So for example, here, if I have this galaxy, I can fit an analytical parameter, like an analytical model with a handful of parameters to capture like the shape of this galaxy, like its light profile, and it's going to be a pretty good fit. The problem is that when I have higher resolution, like better data, like this one here, clearly that's just not going to work. And so the question is like, what do we do now? The problem is that like as the data is getting better and better, it's becoming more and more difficult to come up with complex enough analytical models to capture all the information that's in the data. So the point that I'm going to make is that basically we can learn those more complex parameterizations for our models with in a data-driven way with machine learning, and more specifically with generative models. So this is my game plan for the talk. So we'll see how far we go. But to make things more sort of concrete, I'm going to use a specific example, the specific example of strong gravitational lensing. But a lot of the methods that I'm going to be talking about, they're more generally applicable to a broad range of problems in astrophysics and cosmology. All right. So because I'm going to talk about strong lensing, let's introduce strong lensing. So strong lensing is basically an astrophysical phenomena. So it's the formation of multiple images of some background source of light due to the deflection of its light rays by the gravity of some foreground structure. So let's say that here we're on the Earth is there, and there's two galaxies, one right behind the other one. So there's a blue galaxy sitting right in front of the red galaxy. So as the light rays of the background galaxy pass near the foreground galaxy, they get bent by its gravity, and so they come to us from different angles. And so as a result, here on the Earth, we can see multiple images of the same background galaxy, like this. So it's a little bit like looking at a fish from the corner of a fish tank. So if you've ever noticed, you can see multiple images of the same fish. So here's Mr. Mango demonstrating this effect. This is the coolest video of the whole conference, I can guarantee. So yeah, so you see as he comes to the corner, you can see two images of the same fish. And you laugh, but it took me like a really long time to get this video. Okay, so yeah, so it makes images that are really similar to actual images of strong lenses that we see in the sky. So here we can see two images of the same background galaxy in blue because its light rays have been bent by the gravity of the orange galaxy that's in the foreground. So here's another example of a strong lens. So we can see that the background galaxy that is blue gets like wrapped around the image of the foreground galaxy in orange, and it creates those arcs. So those arcs are actually a really common feature of strong lensing, and that's because of the geometry of the lens. So you can reproduce an effect like this at home with a wine glass and a candle. So if you look at the flame of a candle through the foot of a wine glass, you can see that as they become aligned, the image of the flame of the candle gets wrapped around the foot of the wine glass, and it makes an image that's really similar to actual images of strong lenses that we see in the sky. This is a really cool party trick. But like beyond that, it's actually a really useful phenomena to do a lot of science. So there's a lot of really cool science that we can do with strong lensing. So yeah, just before that, just to make it like absolutely clear, because I'm going to use this analogy again and again, the flame of the candle in this analogy is the background galaxy whose image is getting distorted, and the foot of the wine glass is the foreground galaxy that's distorting the image. Okay. So, like, of course, in the case of like strong lensing in the sky, it's the gravity that's causing the deflection as opposed to refraction in the foot of a wine glass. Okay, so the kind of sciences that we can do with this is like there's a lot of them. So I'm just going to give a bunch of examples. So first, we can use it to study the foot of the wine glass itself. So that's because it's the gravity of the matter that's bending the light. So we can reuse it to map out how mass is distributed in lensing galaxies, regardless of how it emits light. So it's really useful to map out the distribution of matter, specifically like dark matter, in lensing galaxies. So the way that we do this is, let's say, like in the wine glass analogy, if there were a droplet of water on the foot of the wine glass, it's going to cause an additional level of distortion of the image of the candle, and we can use that to basically infer the presence of the foot of the wine glass. So if there were a bunch of dark matter subhalos inside the host galaxies, we'd be able to detect them using this effect, because they would cause an additional level of distortion. So that's the thing that I'm the most interested in. But we can also use it as a cosmic telescope to study the flame of the candle, so like the background galaxy. So that's because lensing magnifies the images of the background galaxies, so we can use this phenomena to study galaxies that would otherwise be below our resolution or sensitivity limits. So we can use it to study like the formation of the earliest galaxies in the universe, for example. Another thing we can do with strong lensing is use it to do cosmology, so specifically to measure H0. So the way that this works, well, one of the ways that this works is that because the light that forms the different images that we see here, there's like 4 images of the same background Etienne, they travel through different paths in space-time. So those different paths, they can have different lengths. And so if the background source has some time variability, that's going to show up as a time delay between the different images. And we can use that to relate to different distances that light has traveled. And so that's how we can use it to measure distances, and that's related to the current expansion rate of the universe. So this is a bunch of science that we can do with strong lensing. So I mentioned before that lensing is like, this phenomenon is a really good example to develop machine learning methods to analyze data. So the reason for that this is like really the perfect problem, is because first of all, it's a probe that's sensitive to a lot of the science we want to learn about. So for example, like strong lensing and like for example, the presence of dark matter subhalos. And we know that even existing data, like even data that's like 10 years old or 15 years old, is already sensitive to the presence of dark matter subhalos. So we have sensitive data already. There's a lot of lenses that we know about, and we're about to discover a whole lot of new strong lenses. For example, with Euclid, LSST, and maybe the Roman Space Telescope, we're expecting to discover over 200,000 new strong lenses. So there's going to be a lot of data to build a lot of statistical significance about the things that we want to learn about. And then the third thing is that as opposed to cosmology, like we just talked about, where the forward model, like the physical model, is really expensive and really difficult and not really known completely, here we absolutely understand the forward model. It's just GR, bending of light, we understand how it works, and it's really fast to simulate. So at this point now you may think, well, we have data that's sensitive, it's been hanging there for like over 10 years, we have lenses, and we know how to simulate things, we understand the forward model, so why has this not been done already? Like we should just be done and go home. But the problem is that we don't have good analysis method to extract the information from the data. The bottleneck is really at the level of the analysis methods. So just to give an example, this lens that I showed before, the horseshoe lens, it's like you go on Wikipedia, that's the example of strong lensing. This is an image that's been taken over 10 years ago, and to this day there exists no good lens model for this lens. So this is one of the best lens models that's been published. So this is the background galaxy. Does not look really like a galaxy. And the residuals are here, and we see that the best fit model is an absolute terrible fit to the data because there's really high residuals. So we don't really have a good lens model, even for like the most well-known lens out there. So how's that even like possible? So like, of course, when we have really like simple data, like really low resolution, then we can fit this data with really simple models. So in the case of strong lensing, when I'm talking about modeling the lens, what I mean is that we need to be able to do two things simultaneously. We need to be able to find what is the undistorted image of the background flame of the candle. And we need to be able to, so that's like the background source, the image of the background source. And we need to be able to map out how mass is distributed in the foot of the wine glass. So like the mass of the lensing galaxy. And so if data is really simple, we want to use a really simple parameterization for this. So we could use like a Gaussian blob for the flame of the candle, like just, blob of light, and like an elliptical blob for the lensing galaxy. So we could do this with a handful of parameters. So in this case, mathematically, the inverse problem we're trying to solve has this form right here, where y is a vector of noisy data. So it contains all like the noisy pixels that we observed. L and S are the handful of parameters that describe the lens and the source. And F is some nonlinear forward model that maps those bunch of parameters into the data space for the lens image. And N is some vector of additive noise, and usually it's Gaussian. It's assumed to be Gaussian noise. So in the case of the data that I showed before, we can fit this model to the data and sample it, and we get like a posterior that looks like this. And we kind of think that we're doing an okay job because our residuals are pretty good. So we've managed to, with this simple model, to basically capture all the information that was in the data. So this is real data, so I cannot like compare to the ground truth. But what I can do is I can use this best fit model to predict what higher resolution observation would look like, and then go take that data. And then if I do that, this is what I get. It's a really good fit. So we think that we're doing a good job here. So that's when like the resolution is really low. So simple model can fit pretty well. The problem is that if instead of this, I have higher resolution observations like here, and I start to resolve structures in my arcs. So then my simple one blob background source is not going to be complex enough to capture what I'm observing anymore. So what we can do, we can say, okay, so I need a more complex parameterization for what my flame of candle is. So I could use a pixelated image. So I could say every single pixel in the flame of my candle image is going to be an independent parameter. And so if I do this, then my problem becomes actually a linear inverse problem in my source parameters in the flame of the candle pixels. See here, y is again the vector of noisy data. X is a vector that contains the pixel values of the undistorted flame of candle. And then it gets multiplied by some lensing matrix L, where the lens parameters, so the parameters that describe the mass in the foot of the wine glass, enter non-linearly to say what this matrix is. So that's, and then N is noise. So this is really good. because I've managed to transform a nonlinear problem into a linear problem. So that should make my life a lot easier. The problem is that, let's say I want to apply this to like data, I cannot just apply this straight out of the box because my problem is now hugely under constrained. Because I have, let's say I have like a 10 by 10, I want to reconstruct the image that's in the middle here. This is the background source. So let's say I have like 100 by 100 pixels in this image, that's 10,000 free parameters that I have. So if I want to regularize this problem, I need to introduce a prior over the background source pixels. And if we're pre-machine learning, the best thing we can do is to use a Gaussian prior. That's basically going to constrain the 2-point correlation function of the background source. And if I do that, the best fit model that I get is this here. So that's okay-ish. It's not great. There's a lot of noise that's leaking in the reconstruction. And the reason for that is that my prior is misspecified. So basically, Gaussian random field is a really poor representation of what a galaxy looks like. And that's what's causing like these problems here. So here I've assumed that I knew what the lens was. I've assumed that I knew what the foot of the wine glass was. And I'm just trying to infer what the background source looks like. But let's say like, okay, what I really want to know is something about the lens. So I don't really care about the background source. So I'm going to move on and try to do the joint inference of the foot of the wine glass and the flame of the candle with this prior to see what happens. All right, so in a lot of the examples that I'm going to give, my background source is going to be an MNIST digit because it makes it really clear to see what's happening because we have a good intuition for what like numbers should look like. So this is an MNIST digit, and I know that it's been lens, and this is my mock observation. So I'm going to try to model it with this like parametric model for my lens and my pixelated image for my background source. So I go in the MNIST data set, I measure the 2-point correlation function of the images, and I use that as a prior. So this is the fit that I get. So looks okay. If I look at the residuals, they're good, but they're not like perfect. And so if we look more in details at the posterior, we see that like parameters specifically like the slope of the lensing potential, this potential here, this parameter here is biased. So what's going on here? So what's happening, if we look at the ground source like background number, that's what it is. So what's happening here is that because I'm using a misspecified prior on my background source, it's zero-centered. So it's trying to make the background number as small as possible so that all the pixels are as close as possible to 0. So it's biasing the size of the background source towards 0. It's making the number smaller. It's still a number, it's just smaller. But then there's a degeneracy between the size of the background source and the slope of the lensing potential, which is this parameter here, and that's what's causing the bias. So the point of this, so that was a lot of technical terms, but the point of this is that I want to do like science with strong lensing. And if I have a biased prior on my background source, what's going to happen is it's going to bias all of the parameters I'm trying to infer. So it's going to bias all of the science that I'm doing with strong lensing, and I'm not going to know. Because here, there was no machine learning here. I'm just sampling, right? It's just like regular, like traditional analysis methods. So what this means is I need to find a way to get an unbiased prior for what a background galaxy looks like. And so one way we can do this is to use data-driven methods. So can we learn this prior, this high-dimensional prior over what galaxies should look like just from images, say, of local galaxies that have not been lensed? So it turns out that if I want to sample a distribution, like when I'm like sampling, the only thing I need to know, well, I could know the density, but I could also get away with just knowing the score of the density, which is the gradient of the log probability. And the reason why this is important is that the gradient of the log probability just contains local information about the distribution as opposed to like an overall normalization constant. And it means that because it's just local information about the density, it's really easy for a neural network to learn. So I can train the neural network to learn this quantity, the score, very easily. And once I know it, I can just use like regular sampling methods to just get new samples from my distribution. So I don't have time to go in, this is just score-based modeling, basically. I don't have time to go into details of how this works, but we train this neural network with denoising score matching, and then once it's done, we can basically, we know the score from some neural network that like approximates this, the score-based, the neural network approximates the score of the distribution I want to learn, so like the distribution of the galaxies in pixel space, and then I can sample new realizations from this distribution. So basically, I just sample one realization of random noise, and I solve a reverse time stochastic differential equation with Langevin sampling, and then I end up with a new realization of a galaxy that I didn't have in my data set because I learned like how to sample from my distribution. So this is a fake galaxy. It's not a real galaxy. So this is pretty cool. I can now generate fake galaxies that look very realistic. So these are galaxies, and some of them are real, and some of them are not. And I'm not going to ask you to guess because I have no idea which one's which. But yeah, some are. And you can go to this website and make fake galaxies. It's actually really fun. But these are just basically samples from my prior. But that's not what I want. I don't want just samples from my prior. I want samples of the possible galaxies that are sitting behind my lens. I want samples out of my posterior. So I said that if I want to sample the distribution, I need the score of the distribution. So I need the score of the posterior, not the score of the prior. So this is the distribution that I want. But I know about Bayes' theorem, so the score of the posterior can be written as the score of the likelihood plus the score of the prior. So this is the part that I just learned, and about this, we're done. And then I know about my physical model, right? I know about lensing, I know like the lensing matrix and everything, and so it looks like we're going to be doing really well to write this term down, but the problem is that actually it's really intractable to write down. So this is where all the trouble begins because it involves some convolution. So this is the likelihood that I know how to write down, the one that's just there, but then it's convolved by some other function, and it's like a huge mess. So in the recent years, it's been a very active area of research to try to come up with approximations for this term. So there's a bunch of like different categories of approximations that have been developed. The first one is a sort of guidance-based method where you try to find a good approximation for the convolved likelihood, basically. There's other approaches that try to solve this by using variational inference to approximate the posterior directly. There's other methods that sort of do variable smithing, like what we heard about this morning, where you do one step of like posterior likelihood evaluation, one step of like partial prior diffusion, and you kind of iterate like that until you converge. And there's like other methods that try to do sequential Monte Carlo, where you propose a bunch of samples that are kind of approximate, you weight them, and then you keep on going like that until it converges. And so those are a bunch of possibilities. There's a whole menu of things we could try. And the bad news is that there was this paper this spring that showed that actually there's not one method to rule them all. We're kind of stuck with like every different problem in physical science kind of has its own best method. And so there's no like one thing we say, okay, this is the best method, this is what everybody should be using. You kind of have to like go and try different methods for your own problem. So what we do in my group for strong lensing is that we use the first method, gradient-based methods, because that's what we found works the best. So basically, and the reason for that is like, because our forward model is linear for the image of the background source, and our noise is Gaussian, so convolving the likelihood is actually a pretty good approximation to the true likelihood, the high temperature likelihood. So like it turns out that it's a reasonable approximation in our case. So that's what we do. So let's go ahead and try to get samples from our posterior. So let's say that this is my ground truth, and I have no idea how I'm doing with time now. Okay, this is not going well. All right. So this is the background source that I'm trying to reconstruct, and this is my model. So I can make mock observations with various levels of noise, and so basically various level of signal to noise. This is very low noise mock data. This is just pure noise basically. And for every one of those mock observations, I can produce posterior samples. So in the case where the likelihood is really informative, there's a lot of information in my data. So posterior samples, these are posterior samples. They are very consistent with each other because there's very little uncertainty in my posterior, because the data is very informative. But as I'm increasing the amount of noise, there's more information that's been destroyed in the likelihood. So I need prior information to come filling this like missing information. So there's gonna be more variability in my samples. And like specifically in lensing, the central area of the background source is more magnified. So there's more information about that in my data. So this gets consistently reconstructed across sample, but the outskirts of the galaxies are kind of like drowned in noise around here. So they get, there's more variability in those because there's more uncertainties in the outskirts of the background galaxy. And then when there's just no information in the data, I just get random prior samples because there's no information in my data. So this is doing exactly what we want this to be doing. and it's very interpretable as well. Like I can understand exactly where is the information coming from in my inference. All right, so we can say also, how good is this out of distribution? Like what if my background galaxy looks nothing like what I thought background galaxies look like? So I can say, what if it was a 7 instead of a galaxy? So I'm going to use a prior trained on galaxies, but the true source is number 7. So again, I make different mock observations with different levels of noise, and then when there's a lot of information in my likelihood, I can reconstruct the background source with very high certainty, because I didn't need the prior, basically. All the information was already in the likelihood. But then as I increase the amount of noise, there's more information that gets destroyed, and so the reconstruction gets sort of like smoothly interpolated with plausible galaxies, because my prior is a galaxy. So it gets information from the prior to fill in the blank, and so there's more variability in the sort of outskirts of the 7, but then the central part still gets reconstructed, and then when there's no information in the data, I get a random galaxy prior sample because I have a prior that's a galaxy prior. So this is doing exactly what I wanted to be doing in terms of inference. So now we can say, okay, now I assume that I knew what the foot of the wine glass was. What if I wanted to use this to jointly infer foot of wine glass and like background galaxy? Is it going to fix the problem that I had before? And the answer is yes. Now in green is when I'm using this like prior, that's a score-based prior, and it's fixing the bias that I saw before that was caused by a Gaussian prior. So this is using MNIST numbers as the background source, but I can also use that with more complex model, physical model for the foot of the wine glass, and galaxy images as background sources, and then I can also get unbiased inference in this case as well. So this is great. It's looking like we can apply this to data and solve dark matter. But the next point in my talk is not dark matter solved, it's data-driven likelihood. So what's going on? So the thing is that I've assumed that the noise model in my likelihood was Gaussian, but in real data, the likelihood is, like the noise model is very rarely Gaussian. So this is noise from HST, and this is noise from JWST. There's nothing interesting here. This is really just noise. So clearly this is not a Gaussian random noise. There's cosmic rays, there's a lot of like correlated stripes in JWST noise. So the noise model is absolutely not Gaussian. And this is just too bad. I wish there was a way to learn some crazy non-Gaussian model just from looking at the noise like that. But then I just said that there's an exact way to do that. I can just learn like how to do this exact thing just from samples of noise. I can train a score model on just pure noise samples and learn the distribution of noise from data and use that as my likelihood, right? Or use it to generate more samples of noise. So I can use basically patches of noise that have not the signal that I care, train a score model, and then generate new realizations of noise. So this is fake noise from JWST and from HST. And now I can use this in a simulation-based inference framework to get really good simulations of noise if I wanted to. Or I can use it in an explicit likelihood framework by using this model as like my likelihood model. So the way it works is that I just learned the score of the noise model, but I know that my residuals should be distributed like the noise model. And so that's exactly what my likelihood is. So basically in my Langevin sampling, I can use this as the likelihood, but then the score is not the score that I learned. So I just need to use the chain rule to change variable. I get the Jacobian of my forward model, and I'm done. So I can basically sample parameters for data where the noise is really non-Gaussian. See here I'm showing, so this is a real patch of HST noise with an injected lens image, and in blue is what I would have gotten with assuming a Gaussian likelihood versus what we get with the data-driven likelihood in gray. So we can manage to get unbiased inference this way, and we can show that it's actually calibrated. And so problem solved. But this is not specific to strong lensing. Actually, there's a lot of different fields in like astrophysics that have to deal with non-Gaussian noise. And so you can apply this framework more generally to any place where really you have non-Gaussian noise. So we've applied this to gravitational wave parameter inference where you have loud glitches. We've applied this to JWST spectroscopy when you're doing transit spectroscopy and you have 1/f noise that you're trying to deal with that's corrupting your spectra. You can use this to do PSF deconvolution. That was again for HST to do basically super resolution, and then you end up with like images quality that are similar to JWST just from HST data, which is pretty cool. You can use it for interferometric images and things like that. And I'm sure there's a lot more examples, but these are just the ones that we've managed to work on since like a year and a half ago. But yeah, so this is a pretty powerful framework, I think, to deal with very hard to characterize likelihood that are very realistic. Okay, accuracy metrics. So I've shown that basically, like with machine learning, you can now really start to solve inference problems that you would not have been able to solve otherwise. But then the question is like, in these like really high dimensional like parameter space, how do I know that the distribution that I'm really sampling is the true posterior as opposed to something that kind of looks like it, but that's not quite exactly the posterior? So basically, how do I actually define and measure accuracy of my posterior samples in this regime? So to do this, there's sort of two questions that we need to answer. So first of all, like if I have some inference pipeline that works in like potentially high dimensional spaces, how do I assess the accuracy of the pipeline itself, just by itself? And then the second question is, if I have part of this pipeline that's a generative model, like my prior is some generative model, how do I know that I'm actually capturing the distribution that I think I'm capturing? Say with my galaxy prior, how do I know that I'm actually capturing the whole distribution of all the galaxies with the right proportions? So in the recent years, we've had like 2 papers that developed 2 metrics to quantify these 2 things. So the first one is TARP, that came out at ICML in 2023. And so basically, it was a coverage test that was designed with like developing random confidence region in a smart way that allowed us to prove that if we pass this coverage test, we're guaranteed to have a calibrated posterior. So we proved the necessary and sufficient conditions for this test. And the cool thing is that the only thing it relies on is to have a distance metric that works in the posterior. So it scales really well to high dimensional spaces. And it's super simple and it's pip installable, so you should go check it out if you care about posterior accuracy. And then the second question is about, if I have a generative model, how do I know that it's actually capturing the whole distribution that I'm thinking that it's capturing? And this one is a paper that was published this spring, and it's basically a test that quantify what is the probability that 2 sets of samples come from the same underlying distribution by marginalizing over the distribution itself. So basically, you can use it as like a p-value of like, if your null test is that they come from the same underlying distribution, what's the probability that have observed those specific set of samples? And so that also just relies on having distance metrics between samples. And so that means that you can apply it to not just like images, but any space where you can define a distance metric. And it's also pip installable, so it works for, like, we've shown that it works on like protein data and like a bunch of different modalities, like time series and things like that, not just images. So, yep. So you should check it out if you care about accuracy of generative models. And not just like generative model, actually, even if you have just like an emulator, like we heard a lot about in the previous talks, you could check if your emulator is actually capturing the really expensive model that you think your emulator is capturing, to see if you're really simulating the range of possible simulations that you should be with your emulator. Okay, so I have 5 minutes, right? No? Okay. So I have a bunch of things. Do you want me to show you data or to talk about how we tackle out-of-distribution problem? Who wants me to talk about out-of-distribution stuff? Okay, who wants me to show data? Okay, I think out-of-distribution wins. You can ask me about data after. Okay, so I just like spent half of my talk, even more than half of my talk, just talking about how important it is to have an accurate prior, because otherwise it's going to bias everything, and everything's going to be wrong. And I'm saying, okay, we should go take our prior from local images of galaxies. But like, I know that local images of, like local galaxies, they don't look like high redshift galaxies like the one that I have in, like behind my strong lenses. And also, like my local galaxies, they have a PSF that they've been convolved with. They have noise that's been applied to them because I've observed them with a telescope. And so should I worry about that? I say, okay, maybe I'm going to go with simulations, but we know that simulations are not perfect. So clearly, my prior will be out of distribution regardless of what I do. And so should I worry? well, maybe I should worry. But the thing is that like now with like LSST and Euclid, we're about to have about 200,000 strong lenses. So what we can do is we can start doing inference over those background images of galaxies. And then if we see that at the population level, there's a shift between the images that I'm reconstructing versus my prior, I know that my prior is out of distribution because I can measure that there's this shift between the two distributions with PQ mass. And so I can detect it, which is great. And then the second thing we can say, okay, like if I think about this as a population level prior, maybe I can learn it hierarchically, the same way I would learn any like hierarchical variable, right? I can just learn my prior hierarchically just from data. And so basically this is what we would like to do, just learning like the prior hierarchically. But this is really hard because then I would end up with a distribution over score models because theta is the parameter of like my score model. So what we can do instead is like go about this in an empirical base kind of way where I'm just going to pick the model that maximizes the likelihood of my data like this. And then I can iterate over this over multiple rounds of data and again prove that this is going to converge to the right distribution. To a distribution that maximizes the likelihood of the data at the end of the day. So basically we do this iteratively and then, so this is how this works. So, all right, so this is math, but then let's give an example. So let's say that like the real galaxies in the universe, they look like this. They're all blue spirals. And I didn't know that these galaxies, the galaxies look like that. What I thought that galaxies were red ellipticals like this. So these are observations of red elliptical galaxies. So what I have seen before is that galaxies just look like this. So can I learn empirically just from data that blue spiral galaxies exist? Just by looking at lens observations of those of galaxies from the true thing, using a prior trained on this. So what I mean is that if I just have those observations of like lens galaxies like that were made with true galaxies that are blue spirals, using just my knowledge that red elliptical exists, can I learn that there's spirals that exist? Okay, so why does it matter? Well, if I was going to do the inference with my original like biased prior, I would get this inference here over what this background source looks like. But if I had the correct prior, I would manage to reconstruct the background source like in a much more accurate way. And the difference between those two is really just the different priors. Like the only thing that changed is that the first one had the biased prior and the second one had the correct prior. So let's say that I have those observations and then I'm trying to, these are the ground truths. After one iteration of like expectation maximization, I get these inference and then after a couple of iterations, I can manage to learn that there's these more complex structure in that's from the data and I can learn that these spiral galaxies are indeed spiral and they have the correct color spectrum. So this is just using the observation and I've learned that my prior was out of distribution and I've sort of discovered that there were more complex structures in the universe just from data itself. I didn't have to model anything. All right, how am I doing with time? I'm done?
No, well.
You don't have the...
You could go on a couple minutes.
So this works for learning priors, like correcting priors that are initially out of distribution. But then the other like elephant in the room is what about misspecified forward model? We know that like when we're doing simulations, like in cosmology, they're not always 100% accurate, right? So could we use something like this to learn to correct our forward models purely from data? And the answer is like potentially yes, we could do that. So a proxy for this is like for the lens galaxies, in all our simulation we assume some parametric model, but then we know from simulations that like the true mass distribution of galaxies should be much more complex than this. So these are from Illustrious TNG. So these are galaxies that would act as lenses and they clearly have very non-symmetrical distributions in a way that's much more complex than what we can capture with our parametric models. So to test this, basically, I'm going to assume that the true what's happening here? Okay. I'm going to assume that the true universe has like galaxies that are described by EPL galaxies, so like elliptical galaxies, but assume that I only know about spherical galaxies, and then try to learn that in reality galaxies are like could be elliptical potentially. But that's like this is actually the physical model that I'm using to lens the data. So the way that I do this is basically I can map my physical model to an over-parameterized latent space and then apply the same technique to learn the parameters, or like the hyperprior over the latent space, basically. And so if I have this observation, and this is the kappa map, and then with the initial round of bias prior, I'm inferring this biased kappa map that's like very spherical. After one iteration, I can get something that looks a lot more realistic, at least in amplitude, but I still have terrible residuals. So I can do a bunch of different iterations over learning a different forward model, and then at the end of the day, I end up with a model that explains the data down to noise. So I've managed to basically update my forward model purely from data in a way that allows me to capture all of the information that's in the data. All right, so I'm out of time, I'm assuming. So the next bonus thing, oh yeah, so all those simulations were made possible by this team of people who wrote a differentiable lens simulator that's really amazing, and that's really easy to use. So if you're curious about strong lensing, you should go check it out. It's like super easy to get started. And I'm not gonna go through the bonus unless you tell me. But I'm just gonna conclude by saying that like, all the examples that I've used, they have to do with strong lensing, but the same structure of problem of having misspecified prior, having misspecified likelihood, having out of distribution priors or forward models, these are common to like almost every problem in some aspect, and like in astrophysics and in cosmology. And so I think that a lot of the methods that I've talked about are like applicable in different contexts. And also I think that this method of trying to really doing the hard problem of doing high dimensional inference is really the way that we are going to sort of open the black box to try to understand where is the information coming from in the inferences that we're doing, and sort of allow us to like open the black box to really understand what we're doing when we use machine learning as part of our inference. So that's it.
Yeah.
Hello. First of all, I would like to thank the organizers for giving me the chance to speak here. I am a bit surprised, to be honest, because when I submitted my abstract, it was pretty clear that I'm not an expert on any AI or machine learning technology, something that I apply to some pet project that I've had for some time. And also, when I prepared this talk, I was told that most of the audience was not astrophysicists, so I hope there is someone left in the audience, because I prepared most of this talk for non-astrophysicists. I'll try to give you a flavor of what my project and my problem is and what I apply for this. Somehow you should see it as something of applied machine learning to a specific project and a specific problem, which is a sort of subset of what Luisa and the other speakers talked about before me. So something more limited both in scope and in size. In fact, I'm not going to go from clusters and from big objects to individual galaxies. And one thing that is that it's been discussed, but it's important for me to get through it, is the evidence of a component of dark matter over a wide range of scales. Okay, now this has clearly been talked about, but it is important to realize that we see the evidence for something which is not electromagnetically interacting, and it is gravitationally interacting over a large range of scales, and we do not know its nature. So we have very good, we have a plethora of models that could explain this dark matter, which in my opinion, it's better be called transparent matter in a way, because it doesn't interact with light at all. It doesn't even make any shadow. But the important thing is that we see evidence from the data on a wide range of scales. That's an important thing. And what have I done? Okay. And the other important thing about dark matter is that, have we heard about, is that it's essential and it's crucial to the formation of the structures that we see them. Okay, now this is something that's been addressed in the previous talks with simulations, but we understand the basic physics of it. The simulations tend to solve the equations of physics that we know, and in the context of structure formation, we might not know exactly the details of what happens inside the pockets, but the dark matter helps to go from the CMB, so from the small anisotropies of density, so the universe is originally perfectly isotropic and homogeneous, down to a level of 10 to the minus 5. So beside this line, which is the Milky Way, all these little creases in color are a contrast of 10 to the minus 4. So it's the fourth digit. The universe is otherwise perfectly uniform. And these densities, they grow into the structures that you've seen, and they grow into the structures that eventually become the halos that host the galaxies. So we do understand the basic physics. It's gravitation coupled to the physics of the gas. And one important thing, to me at least, is that it's well understood from current understanding of physics that it's normal that these pockets that somehow nurture the formation of galaxies are bigger than the galaxy itself. Okay? These are basically the wombs where the galaxies are nurtured. These transparent matter that interacts only gravitationally drives the collapse of this pocket, and the gas falls inside of it. And since the gas can actually radiate away, it's collisional and it's dissipative, the gas falls into the very center of the pockets. So one of the important pillars of the scenario that we have, and whose physics we do understand quite well, is that we do expect a big halo of dark matter around the small galaxy. The galaxy is only the very center of this halo. This we do understand from fundamental physics. And again, I've done something that I shouldn't have done. And one other important thing is that we do believe to understand, we do believe to understand the formation of the halo and the fact that the distribution of matter in the halo should be something like a power law. Something a self-similar power law over many scales. So if you have a small galaxy and a big halo, say 10 kiloparsec around this galaxy, it's going to be a power law that scales over that distance. If you have something like a cluster, 10 megaparsecs or 1 megaparsec, the halo is going to be self-similar, bigger, more massive, but the shape is going to be the same. Now, we do not understand exactly the detail and what is the exact shape, but we do expect this to be a sort of broken power law. Okay? Now, the exact shape of the halo, and I will come to that later on, is somehow a byproduct or a second-order prediction of our cosmological model on the basis of the understanding of physics that we do have. So it is also important to go back to the way we understand and we know about the presence of dark matter. And this is driven by data. It's driven by data on different scales. And some of these scales have been discussed before, so Lindsten has been discussed in the talk before. I put a question mark because I didn't know exactly what you were talking about. But we know it on scales of megaparsec to 10 megaparsec from clusters. We know it in the CMB, so the first light to be produced in the universe is quite a strong probe of the existence of a component which is non-electromagnetically yet gravitationally interacting. And we know about the existence of dark matter within galaxies like our own, like the Milky Way, or smaller galaxies. So what is the physics that we use to infer the presence of this dark matter is a different thing. We use different physics and different observational probes for different scales. Now, for the CMB is quite involved. It's actually something that would take a dedicated class. For the lensing, we heard about it. It seems like it's really me doing this. And for galaxies like our own, I'm going to come to that. Now, for smaller galaxies, things are a little bit complicated, but the observable are very similar. Okay, so let's go to galaxies like our own or Andromeda. This is actually Andromeda, but it makes the depiction of our galaxy. So the way we see galaxies is very much similar to the way our eyes see. It's just intensity and color. That's something that I remember from teaching biologist, Physics 101. And this is an AI-generated depiction of photometry. Of course, this is something which has periodical intensity, but we basically count photons, okay? And the way we see color is absorption lines. And this offers a bonus, because if we know an absorption line and we see it's shifted, we also know the velocity with respect to the observer that that object has. This might seem trivial, but it actually has an important effect, because when we observe galaxies, like Andromeda, like our own, we learn that these galaxies are spinning. Now, I would like to stop at this point and make it clear that I'm using this as one example of the existence of dark matter. It's not the ultimate one. All the scales play a role, but it's important for my problem, okay? So galaxies spin more or less around their center. And when I talk about galaxies spinning, I'm talking about the visible component of the galaxies, because that's exactly what we can see. So this is data-driven. This is what we see. Now, these galaxies are spinning, and the fact that I can measure the velocity of the galaxy allows me, well, on the one hand, the amount of light that the galaxy emits, beside the spinning, helps me to tail the stellar mass of the galaxy. And this is something I like, because I can know more or less how much is the material that I'm seeing, how much does it weigh. The other thing is that I can tell exactly how the galaxy is spinning, well, exactly, not really, but I can tell how the galaxy is spinning, and this informs me if there is a set of conditions that are fulfilled that I can tell the mass of the galaxy. Because if the spinning is driven by the gravitational field, tracing the speeding and if the spinning is circular, I can trace, through the velocity, I can trace the total gravitational mass. Okay? So it so happens that when I measure the stellar mass through photometry and when I measure the total gravitational mass by spinning, I get a discrepancy. This is one, not the only, one of the ways we infer the existence of a dark component of matter. Okay? Again, this is non-conclusive, but it's important for my problem. This is historically one of the ways we've learned about the presence of dark matter on the scale of galaxies. And of course, what I do is that I fit an extra component to the one produced by the stars in order to recover the total rotation curve, right? So one important thing is that if I want to apply this method, and if I want to apply it to galaxies, and I'm interested in galaxies for the reasons I will tell you about, is a lot of things have to go right at the same time. So the spinning of the galaxy has to be driven by the gravitational field. The gravitational field has to have a certain symmetry. The stellar gravitational field, so the gravitational field generated by the ensemble of stars has to have a specific symmetry, and orbits have to be circular. So in a way, the galaxies for which we can apply this method are a limited sample. Okay? And also, there is one important thing. I really care about the density field or the mass of this field of the galaxy, because this, as I said, is a byproduct of the cosmological model. So when I take this scenario and I fit it in the simulation, the density field that I expect sort of comes out of expectations from the cosmological model on smaller scales. So this is something that you might have seen in the previous talk. So what the distribution of dark matter within the galaxy is an important quantity, and it's ancillary if you want to understand the nature of dark matter through other probes. Okay, now let's go back to the galaxy, and I'm interested in knowing what the density of dark matter is within the halo and how it extends beyond the galaxy itself, beyond the visible part of the galaxy itself. And part of the puzzle is the fact that we are not sure whether this power law is actually completely self-similar, or it depends on the mass of the galaxy and the mass of the halo. Now, the dependence is, again, very little, so it might be the slope might be different or not, but this may actually inform us about the searches for dark matter in our galaxy. So, again, my problem is to infer the dark matter density in any of the galaxies which are outside of the Milky Way. And the way I can do it is to test my method, to use this rotation curve method that I have, trying to understand where this instrument that I've shown you so far is both precise and accurate. And one thing that motivated myself and some of my collaborators some time ago is to realize that if I adopt this method of the rotation curve on the scale of the galaxies, and it's the only environment where I can actually use it, it turns out that I can pretty much tell with good precision what the normalization of this profile is, but I am very much at a loss when it comes to the slope. So in other words, I cannot really reconstruct the dark matter profile within the halo from this method. And I would really like to have a place where I can calibrate this method, but this is usually a difficult job in astrophysics, as we heard. So one of the places where I can actually try and calibrate my instrument, and again, I would like to stress that the input of my method is basically photometry, and spectroscopy is a place where I have things under control, and the place where I can control what's going on. And again, this is a numerical simulation, as you've heard. It's a place where I can calibrate my instrument because I can evolve these perturbations, and this is done by several groups. I can evolve the perturbations from the CMB down to the formation of galaxies. Now, again, for those who are not familiar with the simulation, it is to be understood that simulations do include the laws of physics as we understand them. We pretty much know what is going on into the simulation. There is some calibration up to the point that I want to reproduce observables, such as the thickness of stellar disks, or the thinness of stellar disks, or the number of exploding supernovae in known environments, but the basic physics within these numerical simulations is known, and I can actually put the model forward, okay, from the first simulation, from the first perturbations. And so the important thing is that within the simulation, I both know the mass of the stellar halos, I both know the number of stellar halos, but I also know the distribution of dark matter within, and I know the structure of the halo within. So I can use these as labels for my method. Of course, this takes a little bit more work, but the idea is very simple, and it's something that other people have been working on. I basically take halos within the simulation, I create mock data, and I feed them to machines. And of course, the label is going to be the dark matter density as I know it within the simulation. Okay, so that's a little bit the structure of our setup, which is a very simple problem in a way. And for our setup, we started with a specific set of simulation, which are the illustris, which were mentioned earlier. And of course, the simulation evolves the field from back when the universe was very young up to today. What we're doing is we're concentrating on the local universe. So we take a snapshot at low redshift, that means today. We're looking at the local universe. We take a sample of approximately 3,000 galaxies in the local universe, the distance from 10 to 20 megaparsecs. And we produce mock data for these galaxies. We produce photometry bands and spectroscopy. And we basically label the dark matter profiles, and then we validate and we test our model. So again, a closer look, we have to produce the data, photometry, we have to produce the data and spectroscopy. And what we get is something like this. So we, in the testing sample, we do get a prediction for the dark matter model, which actually fits with what we know being the actual and underlying dark matter profile. This is what we get on a smaller scale, and if you look at it, this is the dark matter density. So on the y-axis, you will have the reconstructed dark matter density, and on the x-axis, you have the actual dark matter density at a given radius for different types of galaxies. So our sample is composed of rotating and non-rotating galaxies, and this is something that convinces us that we're working very well. So if you look at these plots, you will see that at a very low distance from the center, so very in the central parts of the galaxies, the reproduction, the reconstruction of the dark matter profile is somewhat failing. And this is something we do expect from the underlying physics. We do expect the center of the galaxies to be dominated by the stars and not by the dark matter. So we do expect the reconstruction of the dark matter to be more deficient. But if we go in the outer regions of the galaxy, we do see that the reconstruction gets way better and actually gets much better for the galaxies that are rotating with respect to the galaxies that are non-rotating. So the elliptical galaxies get worse reconstruction than the reconstructions, than spiral galaxies. Another thing that we do is, well, along the same lines, we do see now this is all the galaxies stuck together, and we see the evolution of the dark matter profile along different radii. And we do see here, in this plot is clear what I was saying earlier, that spiral galaxies are actually better reconstructed than elliptical galaxies, but still the quality of the reconstruction is very high. And we can also see that the machine is learning with respect to the prior. So it's something that it's telling us that the machine is really doing something, it's not just repeating something void. Now, one thing that we found in the previous analysis, but we didn't stress and we cannot really publish because we cannot publish this statement as it is because we don't have enough statistics, but it does look like that this sort of method works way better than the rotation curve method. And of course, all this is in silico, and we don't have strong statistics to make this claim, but it really looks like the method that we've been using, the method that people are using, is good to reconstruct the rotation curves, but it's probably not the best. So inferring conclusions based on the rotation curve method might have to be revised somehow. So of course, there was a missing slide. Well, anyways, let me get to the end. There's other groups that have been working on it, and I think I had this slide somewhere, but anyhow, I apologize for those groups. The conclusions are that we have built a model that works. This model, however, works only in silico. We haven't exported it to the real universe. So we're getting very exciting features. There is non-parametricity, so the dark matter profile doesn't need to be informed, so the machine doesn't need to be informed about an underlying structure. We get non-parametric reconstruction. We can explain the features that we observe. We get different quality of reconstruction on different types and masses of galaxies. And if we try different types of mock data, we do see a difference. So we can explain our results in quite an understandable way. The questions that I have to myself and perhaps with you is, how can we export this method in the real world? So if we want to use this method that we have been informed inside a simulation package, how can we export it to the real world and make sure that our conclusions have a physical sense? should we test it across different simulation suites? Is there anything else that we could do in order to infer some more sound and solid conclusion? And can we actually learn something about the cosmology and astrophysics of dark matter from this method, which has been built entirely within simulation? So this is questions that I have for you, who are the experts in AI, and this is about it. Thank you very much for your attention.
Well, thank you for giving me the chance to talk here, and thanks for sticking around until almost the end of the day. I hope I can make this talk interesting and that you take something away from it. So today I'm going to talk about compression and simulation-based inference for next-generation cosmological surveys. I hope you're still not tired of cosmology, for those of you who are not, but I'm mostly going to focus on the AI tools, so hopefully this is interesting for everybody. So as we heard, we are going to have an explosion of data from galaxy surveys in the coming years, starting now. And it's going to be massive. We're going to have an increasing number of galaxies and volume of the universe to analyze. And so the goal here is to get as much cosmological information from the latent universe as possible that we can trust. So that's very critical when we are doing physics here, because to claim a discovery, we really need to be sure of what we're talking about. And as we heard before, one of the problems we have to analyze this data is that the latent universe is non-Gaussian, as opposed to the early universe, which was very Gaussian. So then the same tools that we have been typically using for that are not going to work as well anymore. However, still today, the standard methods that make the headline results for the big collaborations analyzing data from galaxy surveys still use these same traditional tools that only capture Gaussian statistics, Gaussian information, and in particular using two-point statistics. So this is still where we are. So currently, if you find any news of evolving dark energy, or there's a claim on discovery, it's going to be coming from that left side of this picture here. So we are not exploiting yet all the information that we could be exploiting from the data. So why are these big collaborations still relying on these traditional methods, right? Well, they are very well established, and the systematics are very well understood. So we've been using them for years, so people trust them more. And so this is a question to reflect for people here, like, where do your work stems from, given these three options? Is it on the right side, trying to get as much information from the data, but it's less applicable to data currently? So it's currently less reliable since it has been applied less? Or is it on the other hand? And I think just to say, I'm not trying to criticize any of the methods, I think they are all worth pursuing, trying to reach using the full information content, going all the way to fulfill inference, and still using the traditional methods. I think they're all valuable. But here today, I'm going to talk about some approach in between, in which we still apply some a statistic that we understand better, like higher order statistic on the data, to capture higher order information that the traditional methods cannot use, but that this already has been applied many times to data and might be easily become the new standard. So in this work today that I'm going to present, the goal is to try to bridge this gap, and try to make this the new standard methods of the big collaborations. So this talk is based on this work that I submitted recently to the archive, and the main goal is to bring analysis end-to-end on real precursor data, so that we are prepared for when the next generation data comes, and we are going to aim to make this the headline results for next generation surveys. So the work that I've been leading is the purple one here, and I'm not going to go into details much of cosmology, what this means, but this is just to show that the results of this work, this is kind of the spoiler of the end, are indeed giving more information than the traditional methods, which in this plot are shown by the blue contours using 2-point statistics. This is work done with many people, and this is the main collaborations, the collaborators from this work. So the framework that we are using is the following. I'm going to go through each of the pieces, but in particular, I will focus on these two, the compression and the neural density estimation, which are the ones that are not possible to do without machine learning. So this kind of analysis are rather new, the stimulation-based inference, because precisely these two components would not be possible to do without machine learning. So I will walk through each of the steps during the talk. So first what we do is, so we have the data, and we are going to simulate the data many times with different input parameters that we want to constrain. So in my case, the data is coming from the Dark Energy Survey, which is an imaging galaxy survey. I will just go through this very quickly. We just take images of the sky, one after the other. This is the field of view of the telescope. And at the end of the day, we have a survey. This is how it lays on the sky compared to with our own Milky Way stars. And this is a big international collaboration from many countries around the world. So with this data, what we can do is build weak lensing mass maps. So these are obtained from measuring shapes of galaxies in these images and doing a complicated process that is not important for this talk. Then we are able to get a map that is basically proportional to the dark matter that is between the sources, these source galaxies, and ourselves. And this distribution of dark matter is sensitive to cosmology and what we want to learn about. So what we do is we have this map on the data, and then we're going to generate thousands of such of simulated data that look exactly like the data in terms of noise properties, in terms of like redshift distributions, everything that we match. And we generate this simulation with different input parameters that we want to measure. And the data, at the end, it has the shape of a spherical, as on the sphere, since we're observing this on the sky. And the native structure of the data is on a hill peaks grid that I will talk a bit about later. So we have that, and then what we are going to do is measure a summary statistic into this. Typically, in the traditional methods, this would be the 2-point correlation function that only captures Gaussian information. So in this work, I'm picking persistent homology, which is a mathematical technique from topological data analysis that systematically tracks how topological features appear and disappear as we vary a threshold in the map. So I'm going to explain this, how it works. So basically we have this map and we apply a threshold and keep everything above that threshold. And then we count two things. We count the connected components, which in this case would correspond to the high density regions of the map or to clusters, since this is a dark matter map. And we keep going with the threshold going down. And at each point, we record where these features appear and disappear. And so we record the connected components, and we also record these holes that appear in the map, which would correspond, in our case, to the low density regions, or voids, where there is no matter. And we do this across our whole range of the map. Why do we use persistent homology? Well, it's a good tool because it captures higher order information, and it captures more information than other statistics, such as just measuring the peaks or the voids at one threshold. Since this is doing it systematically across all the thresholds, it has more information. Also, it allows us to link the data vector to physical structures that we understand, such as the voids or the clusters, so that we are going to have a data vector that if there are systematics that affect only one part of this data, like for instance, we know that clusters are more affected by some baryonic effects. This is just like, say, a systematic that is not in our simulation, then we are going to be able to remove this data if we want. if we don't trust it enough. So it really allows us to interpret the analysis a lot more. And also, we were able to measure this on the sphere quite easily, also on the native data structure of hill peaks. So this is a grid that has equal area of pixels, and this is very commonly used in cosmology. And so we found a code called TopoS2 that already existed on this grid, that is very fast, is validated, and so it really makes it easy for this kind of analysis. Because otherwise, other analyses that were trying to apply some statistics had to do some other tricks, like flatten the data, to apply, for instance, a CNN, and then do patches, or other kinds of different things. So in practice, this becomes quite complicated sometimes. So in this case, this was quite easy. Then, once we have this data vector, it's going to be long, and what we need to do is compress before we learn the likelihood. Because to learn the likelihood, we are going to want to do it in a space where the data is very, the data vector is very short, very has low dimensionality, because otherwise we would need so many simulations to fill the space so that we can learn the likelihood. So this is a crucial step, and it's typically in the current analysis one of the ones that people are having most trouble with, and that is kind of the bottleneck of these kind of problems. So what we do is we use several neural networks to compress the data vector for each target parameter of interest, which we have 4, and we train it with a mean square error loss. So the problem that we have, the challenge is that our data vector is huge. So this is not super important, the details, but just to give you a rough idea, it's like our data vector of the Betty numbers, which is from the persistent homology, has 9,600 points in total per simulation. And then we have 10,000 simulations. And this is because we have 40 points per one Betty number. Then we have different smoothing scales, different redshift bins, different the homology groups of clusters and voids. So it's long. And we want to compress it to 4 numbers. So this is kind of the problem that we have. And we have around 10,000 simulations in the training set, where the input parameters are buried. So we tried first to compress this with a fully connected neural network, as it had been done with other companion analysis for other statistics, but this didn't work very well. The results we were getting were quite a lot worse than what we were expecting. And this kind of analysis had only been done on using persistent homology once before, and in that analysis they used kind of a manual method to compress it, just keeping some very few points using chi-square. So we really couldn't use that method. We wanted to compress the full data vector. So we had to innovate. So what we did was instead to organize the data in a different way and apply a CNN. So we developed a specialized architecture that is designed to efficiently capture the correlations between the different smoothing scales and redshift bins in our data. So in that case, what we put is like we organized our data in a specific way, and then we put in each channel of the CNN, we put the different redshift bins and homology groups, in this case the clusters or voids. And then we chose a specific layer called separable convolutional 2D with a specific kernel size that was suitable for our needs. So we choose a kind of weird kernel size, which is 3.1 of this represented here, which was good because it allows us to first compress each Betty curve separately, so that it gets the correlations from that first before moving to the larger scale. And that turned out that it worked pretty well. And for those of you who maybe are not familiar with what's a separable convolutional 2D, certainly I wasn't when I was doing this. This is also called depthwise separable. It's an efficient approximation that reduces computational cost and the model parameters by separating the filtering and the combination steps of a CNN. So the standard convolutions, how they work, okay, this is a GIF, sorry. How they work is they perform the filtering and the feature combination, feature or channel combination simultaneously. Well, in this case, in the depth-wise separable convolution, you do first a depth-wise convolution, so it's channeled separately, and then you do a point-wise convolution that combines all the channels. And that approach, it turned out to work quite well for our case because it allows the network to first learn the features specific to each redshift bin and to each topological structure like clusters and voids separately, and then combine the information across the different bins. And so that turned out quite well. And a fun fact is that this idea came out of interacting with Claude. I don't know if you use it, but I was like saying, okay, I have this problem, I cannot manage to compress this, blah, 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 blah. And then she said, oh, why don't you try separable convolution too? And I was like, okay. And then I tried it and it actually worked much better than the other things that I was using. So this is another use of AI, I guess, in this project. So this is I give just to compare how they use the normal convolutions and just to show how more efficient they are in compared to the normal convolutions. And this is especially true when you have more channels, which we did in our case. We had 30 channels. And also, yeah, the fact that this was speed up, it really mattered because we had a massive amount of data and using this made the analysis much quicker. Okay, so we had this layer. And then we have another similar layer with a bigger kernel size to capture larger correlations between smoothing scales and redshift bins. And the Betty curves. And then once we have this, we are ready to learn the likelihood. So then we have 4 numbers per each simulation, which are the numbers that we want to measure. And we want to, in this case, learn the likelihood with neural likelihood estimation. So for this, so we have these pairs of this T statistic, which is our compressed statistic, and the input parameters of each simulation, which we know. And so from this is where we are going to learn this likelihood using neural networks and normalizing flows. So we are, in this case, we just used a package that is already readily available, which is actually developed by Justin. So you can ask him all the questions you might have about this. It works very well. And an important advantage, I would say, of learning the likelihood instead of learning the posterior, which is sometimes more typical or more used in the literature, is that if you learn the likelihood, then you can change the prior. You can do this many times, and you don't need to rerun all your simulations each time to do the analysis. So this is, I would recommend that if you do simulation-based inference, go all the way for likelihood estimation, not posterior estimation. It was very useful for us. And then finally, once you have the likelihood, then you can just do your regular Bayesian analysis and run an MCMC with that. And I would say that in that case, this is better than for a regular 2-point correlation function with the standard methods, because then the likelihood is super fast. Typically, these analyses for the traditional methods take days to run the MCMC, because this is also a very high dimensional parameter, and each likelihood evaluated is not particularly fast. But here, then once you have it, you can run this as many times as you want with different priors. And then once you have the likelihood, you just evaluate the data realization, and then you get the posterior. And we did all this analysis in a blinded way, so we only ran on the data once. So we validated the whole method first on simulations, using also a different set of simulations that had independent noise properties. Well, like it was a different set of simulations also matching the noise properties of the data, but it was run differently, and we recovered the truth. And so only then, after passing a few validation tests, we ran it on the data. Okay, so this is getting to the end of my talk. I will put again the results. So again, the results of this work are the purple one. So we are doing pretty good in comparison with the other analysis using other statistics. So the blue is the standard method, only Gaussian formation, and then the Yellow is using other statistics, other higher statistics like third moments, scattering transforms, and wavelets combined. So our method is giving similar constraining power just with one statistic. So it looks pretty promising. And also it's comparing in solid black with just using a CNN on the map directly, on a map level. And you can see that this is similar. You can get similar information. And one advantage in our case is that, like I said, that I think is quite important, is that it makes it quite interpretable, that you can directly connect the data vector to the different physical entities in our map. So you can really control for systematics in a much easier way. Okay, so I'm just going to finish with some outlook and perspective. So what we did here is we proved that doing simulation-based inference using persistent homology as a summary statistic is powerful, is feasible, and is scalable. Is a scalable way of extracting robust cosmological information from weak lensing data. The pipeline that we developed is ready to be applied to upcoming surveys. So we did all the steps thinking not only on the current data, but already going to the next data. So that's why it's important that it's spherical, that it can be fed large amounts of data, etc. And we did all of this in a blinded analysis because we believe that in order to make these methods the headline result, we need to get the same standards that we are doing with the traditional methods, where we are always doing blinded analysis. Also, I want to highlight that it's important to target the tools to the data structure that we have. So, and sometimes that's not easy. We actually, we had to look for this specific TopOS2 code, which we didn't know, and we were looking for weeks until we found it. To borrow the tools that then are going to be ideal for the data, and we had to develop new CNN architectures to tackle our particular case. And just some thoughts on what is it going to take to make this the headline result of the big collaborations. So I think we are not there yet. I think what is needed is more testing against systematics. So we have validated our method against the best available simulations that have effects that we don't incorporate, but these are limited. And the traditional methods have a much wider range available to them to test against. So it would be important to develop different simulations with different such of these methods incorporated so that you can check that you're robust against this wider broad of effects that we are still not able to do in our case. And this is going to require building more and better simulations. I think another important point is that we need to develop simulations with other models. So in this case, I'm constraining a given model of the universe, but eventually what we want to do is model comparison. So we want to check, is this the correct model or is this the correct model? So we need simulations with all of those. And anyways, in case we don't get there, this is still useful as validation since it uses completely different methods as the standard tools. And so I think it should still be pursued. So thank you for your attention.
Yeah, so please, Ashik. So too bad you couldn't make it here to Stockholm, but we are ready here to listen to your talk. So take it away, please.
Thank you so much. Yes, I deeply apologize for not being able to make it. That was my intention, but logistics just got in the way. But I am very excited to talk to all of you about some new work in the direction of AI-assisted particle theory design, and most of this talk is going to be based on this paper that I'm linking at the bottom. So physicists build mathematical models to try to understand the universe. Of course, all models are wrong, some are useful. So what defines a useful model? In my opinion, the model needs to be predictive in some sense. For example, in addition to explaining all the data that was used to design the model, maybe it can also make new predictions or extrapolate. Like the best example you can think of is general relativity, which not only reproduces Newtonian gravity in the right limits, but also predicts a correction to the perihelion of Mercury, and predicts completely new things, for example, black holes or gravitational waves, which over the next several decades we've been able to confirm. So this is an amazing theory. Particle physics theories tend to be more messy, so you need to do a lot of back and forth with trying to come up with models that can explain the data. But you'll see that nonetheless, we have a theory that basically explains all the visible matter in front of us. So anything you can taste, touch, feel is explained by the standard model, and this is in front of us. So you have the quarks, for example, they can make up the protons and neutrons. You have the electrons and its cousins. You have the force carriers on the right, and the Higgs boson, which gives mass to all the other particles in this standard model of particle physics. And interestingly, this little cute expression with 4 lines, that is the standard model. So this is what explains everything that you can touch and feel. Of course, if you expand it out, it gets a little bit hairy, but it's still a very impressive and predictive theory. For example, you can go and do all kinds of experiments and test the theory predictions, which are the gray bands on the right you see, compared to the experimental measurements. And time and again, we've tried to break the standard model, and it turns out that, at least in these kind of measurements, the data does agree with the theory. You can go and do more tests, and it's kind of hard to break the predictions of the standard model. And that's kind of surprising because we do know that it's deeply flawed. It can't explain 85% of all the matter. So this is not visible matter, but rather dark matter. It also doesn't tell us why there's more matter than antimatter. It's a very fine-tuned theory where the parameters have to have very specific values for cancellations. And of course, it doesn't explain why neutrinos have mass and why they oscillate. So these are very light particles represented by these new tau, e, and mu that I've shown at the bottom, and turns out that they oscillate from one of them to another, and this is not explained by the standard model. But it's not easy coming up with theories. The space of mathematical tricks you could be using is really ginormous. To give you an example, our previous theory, in the previous theory, we didn't know how to give mass to particles like the Z boson or the W boson without violating very important symmetries, right? And luckily, this problem was solved by something called the Higgs mechanism. And in my opinion, this is quite an unintuitive mathematical trick that was used. You can introduce a new scalar field that affects the other fields in a strange way. It can turn long-range interaction into short-range interaction and give massless particles something that feels like a mass. And so this was a nice trick to give all of these other particles mass. But the idea really was inspired by research that happened in superconductivity in the 1950s. Right, so you might wonder, would particle physicists eventually have figured it out on their own that you could introduce this kind of an extra field to give the others some mass? Maybe, eventually. But it does beg the question, what if solutions of current open problems are also in other non-intuitive mathematical tricks that we just haven't thought to explore? For example, we can think of neutrinos, which are massless in the standard model. We can't explain their oscillations with the standard model. Of course, there are other theories that are out there that can explain these things, but it is a good testing ground for automated theory design. So how would you go about building your own favorite new particle physics theory? To do that, you need to make some choices. You need to choose what fields and symmetries are going to be in your universe. A choice of a field is like adding a new particle that exists in your universe. You can add as many particles as you want, as many fields as you want, but the more fields you add, the more flexibility you give to your model. So if you have 100 fields, you can basically explain all the data in the in your measurements, but nobody's going to take your theory seriously because it's too flexible. Adding symmetries adds structure to your model. It provides restrictions, says that certain fields transform together in certain ways, and it reduces this flexibility but makes the whole theory much richer. Right, so you can introduce these symmetries, for example, using these symmetry groups, for example, SU2, and then you have representations of these groups, and you can place fields in these representations that determine how the fields will transform. You could use SU2, of course, you could use something called SU3, which looks a bit different, and there are a whole bunch of different groups you could use There are like cyclical groups. We show all kinds of different funny. We like to draw them in geometrical shapes so that we can tell others that we actually understand what's going on. But really, there's so many groups, and we really don't understand how to use them in any deep way. So it could take months for someone to build intuition about a particular group, about its symmetries. And so it's quite a risk. If I ask someone to look into a new group, it might take them 6 months to get a feeling for it. And then they might realize that, okay, this is a dead end. There's nothing useful we can build with this group, right? So this is why if you look at neutrino models, you have a whole bunch of them coming out over the last 20 years, and they all use essentially the same 2 or 3 different kinds of groups. And in fact, particle theory design has traditionally been artisanal. There's a personal taste. Someone falls in love with a symmetry group, and they want to use that to explain the universe. So they come up with some theory, make predictions of that theory, and see if they can fit experimental data using that theory. But then there are so many symmetry groups that go unloved and therefore unexplored. So would it be more efficient to have an industrial approach, a systematic search through this high-dimensional space of possible theories to really come up with new ways to explain what we see? To do that, we would need an end-to-end automated pipeline, which we did design by building out physics software that can solve each of these different steps. So you can make a choice of a field and symmetry, make any choice, and then the software will compute the Lagrangian for you. This Lagrangian encodes all the laws of physics that the theory will predict, and then from there you can actually compute the predictions of this theory, look at the elegance of the model. You can then run additional code to compare the predictions to the observed data, do a statistical fit, and then evaluate for yourself whether your theory fits data well or not. But not just that, is it fine-tuned? Does it have too many free parameters? These are all evaluations you can do. And if you were to just randomly pick some fields and symmetries, chances are you wouldn't do very well, because the space is very large and the fraction of good models in them is tiny. And in the end, you want models that have only a few free parameters and have good compatibility with observations. Right? So how can you do this search in a more intelligent way? That's where the AI comes in. So we designed a reinforcement learning based method to search through the space. So your agent here takes an action. So it picks some fields and symmetries, and then it asks our math software that we wrote by discrete to compute the Lagrangian. From there, you can use physics software to compute the physics observations you expect to see in experiments. And then you can use a statistical package to compare these predictions to the observed data. That allows you to then compute some kind of a reward function for the agent. If the fit is good and if the free parameters are few, maybe it gets a higher reward. And hopefully, over many iterations, the agent will learn to design some interesting theories. That was the idea. We applied it. And turns out the agent does learn to design good theories. In fact, too many of them. Here we can see how on the x-axis, as you go through the search, as the agent is learning more and more, it starts to produce better and better models. The blue line shows you the inverse compatibility, so the chi-square of the predictions compared to the data. So the farther down it goes, the more compatible your theories become. But also the number of free parameters goes down, because that's something we encourage the agent to do. So it's able to generate better models with fewer parameters. We can also see that the fraction of good models it comes up with increases as a function of time, so it gets cleverer and cleverer at designing these models more frequently. And what does good models mean? We define it as models that have 7 or fewer free parameters and have a chi-square of less than 10. So this black region, this dashed out region that you can see, better models are going to be further down and to the left. So this is a search in a space that is very well studied by theorists, A4, Z4. And we do find that the agent rediscovers models that are of the same form as what human design or physicist design models you can find in literature over the last 20 years. So that's good. It convinces us that things seem to be working fine. And then you can add a bit of flexibility. You can say instead of Z4, now the agent can choose whatever Zn symmetry it wants to use. And we can see the learning still works. In fact, the number of parameters goes up, so it seems to add more fields earlier and then adds more structure to bring the number of free parameters back down. And the fraction of good models goes up. And in fact, we can see now this area of good models seems to be much better populated. That means that we are starting to see more good models when the agent has a bit more flexibility to play around with different kinds of groups. So this is starting to get interesting. This is still a space that has been explored before. But at this point, you might be curious. So this is all like high-level statistics. What does an individual model look like? So it looks something like this. In this model, the two groups that are coming into play is A4 and Z7. On the top row, you can see the different fields the agent has chosen. So here you have the Higgs doublet. The agent has chosen to have only 3 flavons. It could have had more. The right-handed neutrino, lepton singlets, lepton doublets. If this all doesn't make too much sense to you, it doesn't matter. It's just to show you an example of the kind of theory it can come up with. If you had sat down and tried to come up with a theory yourself using these symmetry groups, you would probably have come up with something similar. So this is not something crazy. It seems to be quite reasonable. And since things work, you can then start to get more ambitious and say, how about now exploring a new symmetry group that I've never studied, nobody's ever studied before for neutrino model building. So that is the T19 symmetry that I'm going to show you next. And this is precisely at the point where you might, if you had to do this manually, you might say, I don't want to spend a few months exploring this thing. It's a high-risk project. So just letting an agent do it for you is quite nice. So we see that the curves still look quite encouraging. The number of free parameters starts to go down. The fraction of good models seems to go up with search time. So let's actually look at the distribution of good models. So this is super encouraging. We see that in this new symmetric group, there is really a rich landscape of viable neutrino theories that had never previously been studied. They have different structure. And we can see, in fact, that this good model space is even better populated than before. But that you may not believe that. What if all of these models that the agent is finding, they're essentially the same? How do we know that they're unique? Maybe the agent is just dressing them up a little bit to make it look different. So we need to do statistical analysis to really understand the distribution of these models. So one easy thing to look at is the number of flavon particles the agent decides for the different good models. And we can see that some of these good models have only 1 flavon, some have up to 6, and there's a nice spread. We can also look at the kind of vacuum expectation value assignments the agent is using, and we see that it uses a whole bunch of different ways of designing these models. And the most important thing is to look at the representation assignments for the different fields. It doesn't just give the same field the same representation or very similar representations each time. You can see that there's a full distribution. For example, if you look at the orange, these are the neutrinos, and they're sometimes in these kind of like 1 representation, sometimes in the 3. So it's really different ways in which you can design these kind of models. So with T19, this new symmetry group, there seems to be genuinely a lot of different ways you can design neutrino models that are compatible with data and have only a few free parameters. Right, and then you can also study things like the flexibility and the fine-tuning of individual models. Of course, we're looking at hundreds of models, so we have to pick one. And I've picked one that has only 4 free parameters. It's tiny, because that makes the visualization a lot easier. So here we can see the 4 free parameters, alpha 1 to 4. And how the correlations are. And if you were to change the free parameters from their best fit values, how would the chi-square vary? So if you had tremendous fine-tuning, you would see that if you change it even a little bit, the chi-square just explodes. That's not what we see. So this seems all right. And there is some correlation between the free parameters. That's all right. And there are a few other diagnostic tools that we develop also here to try to understand what's happening in individual models. And long term, we can think of plugging these kind of diagnostic tools also into the training loop so that the agent has more ability to understand what's happening with each of the individual models. We can also take a deeper dive into what the agent is actually doing over time. So to visualize things, we need to somehow collapse the high dimensional space into something we can look at. So we use an autoencoder to compress the mathematical space into two arbitrary latent dimensions, which are shown here. And so these colorful dots in the background are the different models you could have come up with if you just randomly came up selected fields and symmetries. And the black dots are the trajectory of an individual agent. So in the early stage, you can see that the black dots are all spread out. So it's like randomly sampling from different parts of the phase space. Then through the middle and late middle, it starts to hone in. And you start to see more of these pink dots come up. The pink dots indicate models that are actually good and worth the search. And towards the late stage, you can see that the black dots have really shrunk into small, narrow spaces where it actually does find good models. So it really does learn which spaces to focus its computational power in. Yeah. And you can also notice that even though in the early stage it's spread out, it doesn't focus too much on the extremely low 0-parameter models because, of course, they're just not good enough. They can't predict even that the electron has some mass. So those kind of models are quite ruled out quite early in the training. So what's next? Of course, this is all exciting. In the neutrino world, there's many more things to do. You want to introduce something called modular symmetries, which are the state-of-the-art way of designing neutrino models nowadays. And with that, you can actually start generating really the state-of-the-art neutrino models using these kind of reinforcement learning agents. We also want to introduce more sources of data, experiment data, data from cosmology that we can use to further constrain the search space. And of course, you want to introduce more testable predictions, predictions that the agent will make that are different from one model to the other, and these kind of differences can be tested in upcoming experiments. We also want to enhance the evaluation of these models in different ways, for example, over flexibility, really trying to see if a model could have fit any data, or is it really good only for the data from our universe. But besides the neutrino world, the idea here is to really have AI-assisted theory design. So for that, we have some more general questions we need to answer. One is, what are the patterns the agent is able to exploit? Clearly, it's learning some pattern in this high-dimensional space, and we'd like to understand what that is so that we can really learn these kind of heuristics for designing models from the agent. We don't just want the agent to be a black box that designs these models for us. We want to learn the tricks. Maybe if you put one of the fields in one kind of symmetry representation, then another field necessarily has to go in a different one. So these are the kind of tricks we want to learn, and for that we'll have to design more interpretable algorithms. Also, in terms of algorithmic development, we want to scale to more complex physics simulators, for example, Monte Carlo simulators and so on. And for that, we need to make the algorithms smarter. And of course, explore other theory spaces. Besides that, we also want to combine these kind of ideas with precision theory calculations. There's in quantum field theory, if you want to compute, let's say, these two gluons going to some A particle here, there's one simple Feynman diagram, but there are higher order corrections where you have funny, loopy things in the middle, and you can have a whole bunch of different corrections. And these become very quickly impossible to compute manually. And so there's a lot of work going on in optimizing these kind of higher order calculations also with AI. And it would make sense to combine these kind of ideas together to try to have even more elaborate automated exploration of particle theories. So with that, I come to my conclusion. I hope I've shown you that the space of theories we've been exploring till now manually is a vanishing slice of the entire space we could be exploring. And with AI or reinforcement learning, we can really search more quickly in the space and test new ideas out that would have otherwise required investments of like months of time for an individual person. And this allows us to find new ways of designing theories, like with the T19 group for neutrino model building. And we've only scratched the surface. There's all kinds of new things to do, like testability, interpretability, and also want to plug that there's a growing group at Georgia Tech. In my group, there's even a postdoc opening, and there'll be many more opportunities in the future. So overall, I like to joke that back in the day, we had to wait for an apple to fall on Newton's head. So now, hopefully, we'll have a systemized way of searching through the space, finding all the apples, and finding the next breakthrough in a more systematic way. Thank you.
Do we have any questions? Yes.
Hi, very interesting presentation. Could you please elaborate on what was your intuition behind using reinforcement learning for this and not something a bit more static like Bayesian optimization? What is the MDP essence of this problem that makes it a decision kind of sequential process?
Yeah, that's a good point. We could have used things like other search algorithms. The reason to use RL is a couple of things. One is it's not just for this problem, right? This is we're trying to build out something that will scale, to much more complicated physics software. So this has a little bit of it where the loop doesn't just run the full analysis each time. If the model is obviously bad, then the agent, what we want is for the agent to decide that, okay, I don't even want to do the expensive statistical test. I want to do a very quick, cheap statistical test and see if the model is useful. If it is, then I can run a more expensive algorithm. So long term, we can see that being like, I want to do Monte Carlo simulations, but only for a very small fraction of the theory models that I actually want to search. And these are the kind of things that you can do with RL, and I'm not aware that you can do them with other search algorithms, like, I don't know, genetic algorithms or so on. Yeah, and also in terms of interpretability, we are now working. So this work was with just out of the box RL algorithms like PPO, but we are now building out our own algorithms that have we can infuse mathematical concepts into them, and that makes everything much more efficient.
Yes.
So these days, the big AI companies have agents that do science by basically reading the literature and becoming smart more generally. So what would happen if you connect your tool or to those agents, and so they can read a bit about what humans have done, and then they can do a bit of optimization with your tool? That would cut the physicist completely out of the loop.
I think the physicists will never be cut out, because like we are the ones who are we decide what is interesting. But yeah, I think for sure LLM agents is something that can easily be plugged in. Well, not easily, but I think it makes sense to combine with that, and it's something that we are definitely thinking about. Yeah, the best way to leverage the verifiability of our method, where like everything is correct by design, because the physics software does the calculations, with LLMs which have more flexibility.
So a follow-up question on that. So what do the theory behind the physics theory community think about this? What reactions are you getting?
Yeah, that's a good question. So in general, it's been fun. I think. So I'll tell you what the neutrino physics community thinks. They have actually they enjoyed these presentations, and I think our paper is getting cited already as a tool that can make life a lot easier for model builders. So that's the one kind of reaction from the community that actually cares about this. The larger theory community, one of the questions they ask is, yeah, but neutrino model building is like a useless thing anyway. There are too many models. None of them are particularly predictive. So you should instead try to build dark matter model or something else that's actually useful. And that's a fair criticism. And we are definitely working on other things now. Yeah, I mean, there's like, they find it funny sometimes, they find it interesting. Yeah, it's been quite mixed.
Okay, well, I think we've reached the end of the day. Thank you very much, I think, for joining us online.
Thank you, everybody.